Hey guys, welcome back to the channel. Have you ever wondered why light moves the way it does? Why out of all the speeds in the universe there is one that nothing can outrun? Tonight, we drift into that question. Picture this. You're standing on a quiet beach at sunset, watching golden light ripple across the waves. That glow, soft and warm, is moving at the fastest speed anything in the universe can travel. 300 million meters per second. But this isn't just about speed, it's about the fabric of reality itself. The speed of light isn't just a number, it's the heartbeat of the cosmos, the rhythm that time and space dance to. And the most beautiful part, this speed isn't chosen by light, it's chosen by the universe. So tonight, let's take a slow, thoughtful journey into this elegant mystery. Why can nothing go faster than light? And what secret does that limit hold? But before we begin, take a moment and drop a comment. Where in the world are you tuning in from? And what time is it there? Chapter 1. The speed that rules everything. Picture yourself standing in a dark room, reaching for a light switch. In the tiny fraction of a second between your finger touching that switch and the room flooding with light, something extraordinary happens. Something so fundamental to reality that without it, the universe as we know it couldn't exist. Light doesn't just illuminate our world, it defines the very fabric of space and time itself. We live in a universe with rules, invisible laws that govern everything from the smallest quantum particles to the largest galaxy clusters. Most of these laws feel negotiable. Gravity can be overcome with enough force, friction can be reduced, even the seemingly solid ground beneath our feet is mostly empty space between atoms. But there's one rule that stands absolute, unwavering, each like a cosmic constitution written into the very foundation of existence. Nothing with mass can travel faster than light. This isn't just a speed limit for photons racing through space. It's the universe's ultimate boundary, the line that separates what's possible from what's forever forbidden. Imagine trying to run faster than your own shadow, or attempting to arrive somewhere before you've left. That's the kind of impossibility we're dealing with when we consider exceeding the speed of light. But why? What makes this particular velocity 2099 7,092 458 meters per second so special? Why not faster? Why not slower? The answer lies in something more profound than mere measurement. The speed of light isn't just how fast light travels. It's the rate at which cause and effect can propagate through space. The maximum speed at which information can flow from one point to another. The conversion factor between space and time themselves. Think about the last time you watched lightning during a thunderstorm. You see the flash instantly, but the thunder takes time to reach you. About 5 seconds for every mile the lightning struck away from you. Sound, traveling through air, has its own speed limit. But light seems instantaneous, at least over the distances we experience in daily life. Flip that switch, and the room lights up immediately. Point a laser at the moon, and from your perspective, the red dot appears instantly on its surface. Yet, even light takes time to travel. The sun you see in the sky is actually the sun as it appeared 8 minutes ago. That's how long it took the light to travel the 93 million miles between our star and Earth. The nearest star beyond our sun appears as it was over 4 years ago. When you look up at the night sky, you're literally looking back in time, seeing the universe as it was, not as it is. This delay might seem like a quirk of cosmic distances, but it reveals something profound about the structure of reality itself. Space and time aren't the separate, independent dimensions our intuition suggests. They're woven together into a single fabric called spacetime, and the speed of light is the thread that binds them. Change your motion through space, and you change your motion through time. Approach the speed of light, and time itself begins to slow down, relative to the rest of the universe. Consider this. If you could somehow travel at 99% the speed of light to a star 10 light-years away, you'd experience the journey as taking just over a year. But when you return to Earth, you'd find that more than 20 years had passed for everyone you left behind. This isn't science fiction. It's the inevitable consequence of light speed being the cosmic speed limit. Every fundamental particle, every force, every field in the universe respects this limit. Even the universe's expansion, dark energy, and the ripples of gravitational waves that stretch and compress space itself all operate within the constraints imposed by the speed of light. It's as if the entire cosmos operates according to a master clock, and that clock ticks at exactly the rate light travels through empty space. But perhaps most remarkably, this speed limit isn't just a constraint, it's what makes complexity, structure, and ultimately life possible. Without it, cause and effect would become meaningless concepts. The past and future would blur together. The very notion of sequence, of one thing leading to another, would collapse. The universe would become a chaotic soup, where nothing could build anything else, where stars couldn't form, where chemistry couldn't create the intricate dance of molecules that leads to biology, consciousness, and wonder. As we embark on this journey together, we'll discover that the speed of light isn't just a number physicists have measured, it's the universe's way of ensuring that reality makes sense, that time has meaning, and that the story of existence can unfold in a way that allows for growth, change, and the emergence of beings capable of contemplating these very mysteries. So when you next flip that light switch, remember, you're not just illuminating a room, you're witnessing the universe's most fundamental law in action, the speed that rules everything, the cosmic constant that makes existence itself possible. And in understanding why light travels at exactly this speed, no faster, no slower, we begin to understand why the universe is the way it is, and why we're here to wonder about it at all. Chapter 2. What is light? Really? On a quiet summer morning, sunbeams stream through your window carrying with them one of the universe's most beautiful contradictions. Those golden rays that warm your face and cast shadows on the wall are simultaneously the most familiar thing in our daily experience, and one of the most mysterious phenomena in all of physics. Light is quite literally something you can see but can never truly catch. Something that behaves like a wave when nobody's looking but acts like a particle the moment you try to detect it. To understand why light travels at the cosmic speed limit, we first need to unravel what light actually is, and this question has puzzled humanity's greatest minds for centuries. Ancient philosophers thought vision worked by beams shooting out from our eyes, like biological flashlights illuminating the world. It's a charming idea, really, imagining our eyes as tiny suns, but it couldn't explain why we can't see in complete darkness, or why closing our eyes blocks out the world. The truth about light is far stranger and more wonderful than those early theories suggested. Light is pure energy in motion, a self-sustaining wave of electric and magnetic fields that creates itself as it travels. Imagine trying to describe color to someone who's been blind from birth, or explaining music to someone who's never heard sound. Light exists in a realm between the tangible and the ethereal. It has no mass, no substance you can hold, yet it carries energy and momentum, can push solar sails across space, and even bend under the influence of gravity. Here's where things get deliciously weird. When physicists finally developed tools sensitive enough to study individual particles of light, photons, they discovered something that challenged everything they thought they knew about reality. Shine light through two parallel slits, and it creates an interference pattern on the wall behind, just like waves in water would. This makes perfect sense if light is a wave, spreading out and meeting itself on the other side, creating patterns of brightness and darkness, where the waves either reinforce or cancel each other out. But here's the twist that kept physicists awake at night. When they tried to observe which slit each photon passed through, the wave pattern disappeared. Suddenly, each photon behaved like a tiny bullet, passing through one slit or the other, never both. It's as if light knows when it's being watched and changes its behavior accordingly. Not metaphorically, but literally. The very act of measurement transforms waves into particles. This wave-particle duality isn't just a quirk of light, it's a fundamental feature of reality at its smallest scales. But light makes this mystery especially poignant, because photons are the messengers that carry information about everything else in the universe to our eyes and instruments. We study atoms by observing the light they emit, peer into distant galaxies by collecting ancient photons that have traveled billions of years to reach us, and even detect gravitational waves by watching how they subtly change the path of laser light in massive detectors. Think of a photon as a quantum of pure action, the smallest possible packet of electromagnetic energy. Unlike the particles we're familiar with, photons have no rest mass. They don't exist in a state of stillness, waiting to be accelerated. From the moment they come into being, they're already traveling at the speed of light, and they continue at that speed until they're absorbed by something else. They can't slow down, can't speed up, can't even change direction unless they interact with matter or fields. This masslessness is crucial to understanding why light travels at the cosmic speed limit. In Einstein's universe, anything with mass would require infinite energy to reach light speed, an impossibility that preserves the speed limit for massive objects. But photons, having no mass to accelerate, naturally exist at this ultimate velocity. They don't travel at the speed of light, despite some cosmic speed limit. They define what that speed limit is. But light isn't just visible photons streaming from the sun or glowing from your phone screen. The electromagnetic spectrum stretches far beyond what our eyes can detect. From radio waves longer than buildings, to gamma rays more energetic than visible light, by factors of billions. The radio signals carrying your favorite songs, the microwaves heating your coffee, the X-rays revealing broken bones, the infrared warmth radiating from your body, all of these are light, just at different frequencies, all traveling at exactly the same speed through empty space. Every photon, regardless of its energy or wavelength, carries with it a piece of information about where it came from. The light streaming from distant stars tells us about their temperature, composition, age, and motion. The cosmic microwave background radiation fills the universe with ancient light from when atoms first formed, carrying within it the blueprint of everything that would eventually become galaxies, stars, planets, and us. Perhaps most remarkably, light doesn't experience time the way we do. From a photon's perspective, if we can imagine such a thing, no time passes during its journey. A photon created in the core of the sun experiences its 8-minute journey to Earth, and then perhaps its billion-year journey to the edge of the observable universe, as a single, timeless instant. It exists in a state of eternal now, a messenger that connects all moments and all places without ever aging, without ever changing, without ever experiencing the passage of time. This timeless quality of light reveals something profound about the nature of the speed limit itself. It's not just about velocity, it's about the boundary between experiencing time and existing outside of it. Anything traveling slower than light moves through time, experiencing cause and effect, past and future. But light itself exists at the precise threshold where time becomes meaningless, where the distinction between here and there, between now and then, dissolves into pure connection. And so light reveals itself as something far more than mere illumination. It's the universe's way of connecting every point in space and time to every other point. The medium through which information travels, the boundary between the temporal and the eternal. In understanding what light really is, this strange, massless, timeless messenger that defines the very fabric of space-time, we begin to see why its speed isn't just a cosmic coincidence, but the fundamental constant that makes existence coherent, causality possible, and wonder inevitable. Chapter 3. How fast is fast? Understanding feast numbers have a peculiar way of hiding their significance behind their precision. When we say the speed of light is exactly 299,792,458 meters per second, that string of digits might seem arbitrary, like a cosmic phone number dialed by some universal force. But contained within that specific value lies one of the most profound truths about reality. This isn't just how fast light happens to travel, it's the rate at which the universe itself operates, the fundamental tempo of existence. Imagine trying to explain the concept of fast to someone who's never experienced motion. You might start with familiar examples: a walking pace, a running sprint, a car on the highway, a jet streaking across the sky. Each represents a different scale of speed, but even our fastest human achievements pale in comparison to the cosmic velocity of light. If you could somehow run at the speed of light, you could circle the Earth's equator over 7 times in a single second. You could travel from Earth to the Moon in less time than it takes to say hello. But here's what makes the speed of light truly extraordinary. Its precision isn't the result of increasingly accurate measurements. It's a defined constant. In 1983, scientists realized something remarkable. We could measure distance more accurately using light than we could measure light using distance. So they redefined the meter itself in terms of how far light travels in a specific fraction of a second. The speed of light became exactly 29,992,458 meters per second. Not because that's what we measured, but because that's what we decided a meter should be. This reversal reveals something beautiful about the relationship between light and space. We don't really measure the speed of light anymore. We use light to measure everything else. Every ruler, every GPS satellite, every precision instrument depends on this cosmic constant to define what distance means. The universe provides the standard, and we align our human measurements to match its fundamental rhythm. But why this particular number? Why not a nice round figure like 300,000 meters per second? The answer lies in the arbitrary nature of our human measurement systems. Meters and seconds are human inventions, chosen for their convenience in describing our everyday world. The speed of light doesn't care about our measurement preferences. It simply is what it is, indifferent to whether we measure it in meters per second, miles per hour, or any other units we might devise. In natural units, the measurement system the universe would use if it could choose, the speed of light equals exactly one unit of distance per 1 unit of time. This isn't just mathematical convenience, it reflects a deeper truth about the structure of spacetime. Space and time are so intimately connected that they're really just different aspects of the same thing, and the speed of light is the conversion factor between them, like the exchange rate between two currencies that are actually the same currency viewed from different angles. Consider what this speed means in human terms. Light from the sun takes about 8 minutes to reach Earth. Not very long by human standards, but long enough that the sun could explode and we wouldn't know it for 8 minutes. We'd continue to feel its warmth, see its light, live in blissful ignorance of the catastrophe until that final flash of information reached us at the cosmic speed limit. In those 8 minutes we'd be living in a universe that had already fundamentally changed. But the change itself travels no faster than light. This delay becomes even more dramatic when we consider the vastness of space. The nearest star, Proxima Centauri, is about 4.24 light-years away. This means the light we see from it tonight actually left that star when you were about 4 years younger. If you're 20, you're seeing Proxima Centauri as it appeared when you were 16. If you're 40, you're seeing it as it was when you were 36. The star could have dramatically changed, or even died, and we wouldn't know for years. Yet even this cosmic delay seems almost instantaneous when compared to the age of the universe. Light from the most distant galaxies we can observe has been traveling for over 13 billion years, showing us the universe as it appeared when it was just a few 100 million years old. A cosmic infant compared to its current age of nearly 14 billion years. These ancient photons have been racing toward us since before the Earth existed, before the sun formed, carrying within them the baby pictures of the universe itself. But here's where the speed of light reveals its true significance. It's not just about how fast information travels, it's about the maximum rate at which cause can lead to effect. Nothing can influence anything else faster than light can travel between them. This creates what physicists call light cones, regions of spacetime that define what can affect what and when. Every event in the universe sits at the center of its own light cone, able to influence only those regions that light could reach in the time available. This speed limit isn't just a cosmic traffic law. It's what prevents the universe from becoming a chaotic mess, where effects precede their causes. Without it, you could theoretically send information to your past self, creating paradoxes that would make narrative coherence impossible. The speed of light ensures that stories can be told, that events can unfold in sequence, that the universe maintains the logical structure necessary for complexity to emerge. Think of the speed of light as the universe's frame rate, the maximum frequency at which change can propagate through space. Just as a movie creates the illusion of smooth motion by showing us 24 frames per second, the universe creates the illusion of continuous causality by limiting how quickly information can travel from point to point. Too slow, and the universe would feel sluggish, with long delays between cause and effect. Too fast, and causality itself might break down. The beautiful precision of that number, 29, 07 and 92, 30 and 58 meters per second, thus represents something far more significant than a mere velocity. It's the universe's way of maintaining order, ensuring that complexity can emerge, that structures can form, that consciousness can arise, and contemplate its own existence. It's the tempo at which reality unfolds, the rhythm that allows the cosmic symphony to play in harmony, rather than descending into cacophony. And so when we say light travels at 2099 7092, 458 meters per second, we're not just stating a measurement, we're acknowledging the fundamental constant that makes measurement itself possible, that ensures cause precedes effect, that allows the universe to tell its story in a way that makes sense. In understanding this speed, we begin to understand why the universe is comprehensible at all, why patterns can emerge, why knowledge can accumulate, and why we can sit here in this moment contemplating the very speed that makes this moment possible. Chapter 4. the space-time blueprint. Einstein once described his greatest insight as the happiest thought of his life. The realization that someone falling freely wouldn't feel their own weight. In that simple observation lay the seeds of a revolution that would forever change how we understand space-time and the speed of light. But to appreciate why light travels at the cosmic speed limit, we need to step back and consider something even more fundamental: the discovery that space and time aren't the separate, absolute stages we thought they were, but rather two aspects of a single, unified fabric called space-time. Imagine you're sitting in a comfortable chair right now, feeling perfectly still and stable. According to your senses, you're at rest while the world continues around you. But zoom out from your immediate perspective, and a different picture emerges. You're actually spinning with the Earth at over 1,000 miles per hour at the equator, orbiting the Sun at 67,000 miles per hour, racing through the galaxy at hundreds of thousands of miles per hour, as our solar system follows the Milky Way's rotation. Yet none of this motion feels real to you, because you're moving along with everything else in your local environment. This is the first hint that motion isn't absolute. It's always relative to something else. But Einstein's genius was recognizing that if motion is relative, then space and time themselves might not be the fixed, unchanging backdrop that Newton imagined. Instead, they might be more like a flexible stage that bends and stretches depending on how fast you're moving and how much matter and energy are present. The breakthrough came when Einstein realized that the speed of light creates a strange paradox if space and time are absolute. According to Maxwell's equations, the mathematical description of light and electromagnetism, light should always travel at the same speed, regardless of how fast its source is moving. But this seems impossible if you think about it like throwing a baseball from a moving car. If you throw the ball forward at 60 mph from a car traveling 60 mph, someone standing on the sidewalk sees the ball moving at 120 mph. Simple addition. Light doesn't work this way. Shine a flashlight forward from that same moving car, and someone standing still measures the light moving at exactly the speed of light, not the speed of light plus the car's velocity. The light doesn't inherit any extra speed from its moving source. This constancy of light speed seemed to violate common sense, until Einstein realized that our common sense about space and time was wrong. The resolution is as elegant as it is mind-bending. Space and time adjust themselves to keep the speed of light constant for everyone. If you're moving fast relative to someone else, time slows down for you from their perspective, and distances contract in the direction of your motion. These aren't just optical illusions or measurement errors, they're fundamental changes in the structure of space-time itself. Time literally runs slower for moving objects, and space literally contracts in the direction of motion. Think of space-time like a rubber sheet, stretched tight. Place a bowling ball in the center, and it creates a depression. Roll a marble nearby, and it will curve around the depression, following the bent geometry of the sheet. This is how Einstein envisioned gravity, not as a force pulling objects together, but as the curvature of space-time caused by mass and energy. The Earth doesn't pull you down, rather your mass creates a small curve in space-time, and you follow the straightest possible path through that curved space, which happens to be toward the Earth's center. But here's where the speed of light enters the picture, in the most fundamental way. It's not just the speed at which light travels, it's the speed at which space-time itself propagates changes. When you move a massive object, the curvature of space-time around it doesn't change instantly everywhere. The change spreads outward at the speed of light. This is what gravitational waves are, ripples in the fabric of space-time itself, traveling at exactly the speed of light, carrying information about space objects accelerating somewhere in the universe. The speed of light is thus revealed as something far more profound than just the velocity of photons. It's the speed at which information can travel through space-time, the rate at which cause and effect can propagate, the maximum velocity at which the universe can update itself. When Einstein's equations showed that gravity travels at the speed of light, they revealed that this cosmic speed limit governs not just light and matter, but the very structure of space and time. This has profound implications for how we understand motion through space-time. Every object, including you, is constantly moving through space-time at exactly the speed of light. Right now, as you sit reading this, you're racing through time at nearly the full speed of light. If you start moving rapidly through space, some of that motion through time gets converted into motion through space, but the total always remains constant. It's like walking across a field. You can walk north or east or northeast, but you can't walk in more directions simultaneously than your legs can carry you. This is why time slows down as you approach the speed of light. The faster you move through space, the slower you move through time, because your total motion through space-time is fixed. At the speed of light itself, all your motion is through space, and none through time. Which is why photons don't experience the passage of time, and why anything with mass can never quite reach light speed, because it would require infinite energy to redirect all its motion from time into space. The beautiful mathematics of space-time reveals why the speed of light is universal and constant. It's not a speed limit imposed from outside the universe, it's the natural consequence of how space and time are woven together. Just as the angles in a triangle must always add up to 80 degrees in flat space, the speed of light must always measure the same value, because it represents the fundamental geometry of space-time itself. Consider the profound implications. Every measurement of distance involves time, how long light takes to travel, and every measurement of time involves space, the distance light travels. The meter is defined by how far light travels in a fraction of a second. The second is defined by the vibrations of atoms, which depend on the electromagnetic interactions that propagate at light speed. We can't separate space from time any more than we can separate length from width in a rectangle. This unified spacetime isn't just an abstract mathematical concept. It's the stage on which the entire drama of existence unfolds. Stars form when matter curves spacetime enough to collapse under its own gravity. Planets orbit in the curved paths that represent straight lines through curved spacetime. Light from distant galaxies follows the contours of spacetime, sometimes bending around massive objects to create gravitational lenses that allow us to see even more distant objects behind them. And we, in our daily lives, are constantly navigating this curved spacetime without realizing it. The GPS satellites orbiting Earth must account for the fact that time runs slightly faster in their weaker gravitational field and slightly slower due to their orbital motion. Without Einstein's corrections for spacetime curvature, GPS would be off by miles within hours. The speed of light thus emerges not as an arbitrary cosmic speed limit, but as the fundamental constant that defines the relationship between space and time. It's the universe's way of ensuring that these two aspects of spacetime remain properly calibrated with each other, that causality flows in the right direction, that the past stays past, and the future remains future. In understanding spacetime, we begin to see why light travels at exactly the speed it does, not because that's how fast light can go, but because that's the speed at which reality itself operates. Chapter 5. Messengers. There's something almost mystical about masslessness. In our everyday world, everything has weight, substance, the satisfying heft that comes from matter occupying space. Pick up a stone, and you feel its mass in your palm. Push a car, and its inertia resists your effort. But photons, those tiny packets of light energy, exist in a realm beyond mass, beyond the gravitational embrace that binds all other particles to the speed limits of massive objects. They are the universe's ultimate minimalists, stripped of everything except pure energy and momentum, born traveling at the cosmic speed limit, and incapable of ever slowing down. To understand why photons naturally travel at the speed of light, we need to appreciate what it means to be massless in Einstein's universe. Mass isn't just about how heavy something feels in your hand. It's about how much energy is locked up in an object's very existence. What Einstein revealed in his famous equation. Every proton in your body, every electron, every atomic nucleus carries within it an enormous amount of rest energy. Energy that exists simply because the particle exists, independent of its motion. But photons are different. They have no rest mass, no internal energy reservoir that exists independently of their motion. All of their energy comes from their movement through space. They don't have the option of sitting still, accumulating potential energy while at rest. From the moment they're created, whether in the nuclear furnace of a star, the heated filament of a light bulb, or the quantum transitions of atoms, they emerge already traveling at the speed of light, carrying their energy as pure kinetic motion. This creates a beautiful symmetry in the universe. Massive particles can exist at rest, storing energy in their mass, gaining additional kinetic energy as they're accelerated. But the faster they move, the more energy it takes to accelerate them further, approaching infinite energy requirements as they near light speed. It's like pushing a car up an increasingly steep hill that becomes vertical just before you reach the summit. Possible in principle, but impossible in practice. Photons sidestep this problem entirely by having no mass to accelerate. They don't gradually speed up from rest to light speed. They begin at light speed because that's the only speed they can have. Think of them as the universe's perfect messengers, unencumbered by the inertial baggage that slows down everything else. They carry information, energy and momentum from one point to another, without the delays and complications that affect massive particles. This masslessness has profound consequences for how photons experience reality, or rather, how they don't experience it. From a photon's perspective, if we can imagine such a thing, the journey from the center of the sun to your eye happens instantaneously. No time passes during its 8-minute journey at the speed of light. The photon is created and absorbed in what seems like a single moment from its own reference frame. It exists in a state of eternal now, connecting distant points in space without ever experiencing the passage of time that separates them. But masslessness doesn't mean nothingness. Photons carry momentum proportional to their energy, which might seem paradoxical since momentum usually equals mass times velocity. How can something with no mass have momentum? The answer lies in Einstein's more general relationship between energy, momentum, and mass. For massive particles, E equals mc squared when they're at rest. But the full equation is E equals mc squared tro pc squared, where p represents momentum. For photons, with zero mass, this simplifies to E equals c. All their energy comes from their momentum multiplied by the speed of light. This momentum is real and measurable. Solar sails work by catching the gentle but persistent push of photons from the sun. Laser light can levitate tiny particles by bombarding them with momentum-carrying photons. Even the pressure of starlight, incredibly weak though it is, gradually changes the orbits of asteroids over millions of years. Light carries momentum without mass, force without substance, influence without physical presence. The masslessness of photons also explains why they're affected by gravity despite having no mass for gravity to pull on. In Einstein's curved spacetime, gravity doesn't pull on mass. It curves the fabric of space and time itself, and everything, including massless photons, follows the straightest possible paths through that curved space. Light bends around massive objects not because it's attracted to them, but because the massive objects bend the very geometry of the space through which light travels. This leads to one of the most beautiful phenomena in the universe, gravitational lensing. When light from a distant galaxy passes near a massive object like a galaxy cluster, the curved space-time acts like a cosmic magnifying glass, bending and focusing the light to create multiple images. Einstein rings, or dramatically brightened views of objects that would otherwise be too distant to see clearly. The massless messengers follow the contours of curved spacetime like raindrops following the curves of a windshield. But perhaps the most remarkable aspect of photons' masslessness is how it makes the universe transparent to information. Because photons don't interact with each other, they pass through each other without interference. Light from the most distant reaches of the observable universe can travel for billions of years without being absorbed or scattered by all the other light in between. The cosmic microwave background radiation, the afterglow of the Big Bang itself, consists of ancient photons that have been streaming freely through space for over 13 billion years, carrying within them the blueprint of how matter was distributed when the universe first became transparent. Every photon is thus a time capsule, a massless messenger carrying information from its point of origin to wherever it happens to be absorbed. The light entering your eye right now contains photons from the sun, from distant stars, from reflected moonlight, from the warm glow of objects around you. Each carries its own story, its own signature of where it came from and what it encountered along the way, all traveling at exactly the same speed despite their vastly different energies and wavelengths. This universality of light speed, regardless of energy, is another consequence of masslessness. In our everyday world, more energetic things often move faster, throw a ball harder, and it travels faster. But photons, whether they're low-energy radio waves or high-energy gamma rays, all travel at exactly the same speed in vacuum. Their energy differences show up in their frequency and wavelength, not their velocity. A radio photon and a gamma-ray photon racing through empty space will arrive at the same distant destination simultaneously, despite the gamma-ray carrying millions of times more energy. This creates a cosmic democracy of light where every photon, regardless of its energy or origin, travels at the same universal speed. The dim light from a candle and the brilliant flash of a supernova explosion both send their messengers racing through space at 29,792,458 meters per second. The universe doesn't play favorites based on energy or importance. The speed of light is the same for all electromagnetic radiation, from the longest radio waves to the shortest gamma rays. In their masslessness, photons thus embody the pure essence of the cosmic speed limit. They don't struggle against inertia, don't require infinite energy to reach light speed, don't experience time dilation or length contraction, because they define the limit at which these relativistic effects approach infinity. They are the standard bearers of the cosmic speed limit, the messengers that carry information at the maximum rate the universe allows, the threads that weave together the fabric of spacetime by connecting every point to every other point at the speed of light. Through understanding these massless messengers, we begin to see why the speed of light isn't just about light. It's about the fundamental rate at which reality updates itself, the maximum speed at which cause can lead to effect, the universal constant that ensures the cosmos remains causally connected, while preventing paradoxes that would make existence itself impossible. Chapter 6. The cost of acceleration. Picture yourself behind the wheel of a car, pressing gently on the accelerator. The engine responds smoothly, the speedometer climbs steadily, and you merge effortlessly into faster traffic. This everyday experience of acceleration feels natural, predictable. Apply more force, gain more speed, but hidden within this simple process lies one of the universe's most profound truths. The faster you go, the harder it becomes to go even faster. And as you approach the speed of light, this difficulty doesn't just increase, it becomes literally infinite. This isn't a limitation of engineering or a failure of imagination. It's written into the fundamental structure of reality itself. When Einstein revealed that mass and energy are equivalent, he uncovered something remarkable about acceleration. Every time you speed up an object, you're not just giving it kinetic energy, you're increasing its relativistic mass, making it harder to accelerate further. It's as if the universe has a built-in resistance to anything with mass reaching the cosmic speed limit. Imagine trying to push a shopping cart that gets heavier with every step you take. At first, it's easy enough to increase your pace, but gradually the cart becomes more massive, requiring more and more effort to achieve smaller and smaller increases in speed. Eventually you'd reach a point where no amount of pushing could make the cart go any faster, because it would have become infinitely heavy. This is essentially what happens to any object with mass as it approaches light speed. The mathematics of this process are elegantly captured in the Lorentz factor, named after the physicist who first described these relativistic effects. As an object's velocity approaches the speed of light, this factor grows without bound, approaching infinity. What this means in practical terms is that the energy required to accelerate a massive object grows without limit. As its speed approaches light speed, you could harness the energy output of entire stars, and it still wouldn't be enough to push even a single proton to exactly the speed of light. But why does this happen? Why doesn't the universe simply allow unlimited acceleration? The answer lies in the deeper structure of spacetime itself. As we've seen, every object moves through spacetime at exactly the speed of light, but that motion is divided between movement through space and movement through time. When you're at rest relative to your surroundings, nearly all of your motion through spacetime is motion through time. As you accelerate through space, some of that motion through time gets converted into motion through space. This conversion isn't free. It requires energy, and the faster you go, the more energy it takes to redirect a little more of your spacetime motion from time into space. It's like trying to change the course of a massive river, possible at first, but requiring increasingly heroic efforts as you try to make larger changes. The universe's resistance to acceleration isn't arbitrary. It's the natural consequence of spacetime having a fixed geometry that all motion must respect. Consider what happens to time itself as you approach light speed. From the perspective of someone watching you accelerate, your clocks begin to run slower and slower. At 90% the speed of light, your clocks run at roughly half speed. At 99%, they crawl at just 14% of their normal rate. At 99.9%, they tick at barely 4% of normal speed. As you approach exactly light speed, time dilation approaches infinity. Your clocks would appear to stop entirely from the outside perspective. This time dilation isn't just a side effect of high-speed travel. It's intimately connected to why acceleration becomes impossible at light speed. The energy you put into accelerating an object doesn't just increase its kinetic energy, it increases its total energy, which includes its rest mass energy. From the perspective of someone watching the acceleration, the object becomes more massive, requiring ever more energy to achieve smaller and smaller increases in velocity. But here's where the story becomes truly fascinating. This cosmic speed limit isn't just about individual particles or spacecraft. It applies to information itself. No signal, no influence, no cause can propagate faster than light speed. This means that when you try to accelerate an object, the information about that acceleration can't travel faster than light speed through the object structure. The front of a rigid rod can't know that the back is being pushed faster than light could travel from back to front. This leads to one of relativity's most counterintuitive consequences. There's no such thing as a perfectly rigid object. When you push on the back of a ruler, the front doesn't start moving instantly. Instead, the compression wave travels through the material at the speed of sound in that material, which is always much slower than light. If you tried to push something faster and faster, eventually, you'd reach a point where the structural information couldn't keep up, and the object would have to deform or break apart. Real particle accelerators demonstrate these principles every day. At CERN's Large Hadron Collider, protons are accelerated to 99.999999999% the speed of light, so close to light speed that they circle the 27-kilometer tunnel over 11,000 times per second. Yet despite consuming enormous amounts of energy, these protons never quite reach light speed. The closer they get, the more energy it takes to squeeze out even tiny additional increases in velocity. What's remarkable is that these high-energy protons traveling at nearly light speed still can't catch up to the photons of light produced in the same collisions. The photons streak away at exactly light speed while the protons, despite their tremendous energy, lag behind by that tiny but insurmountable margin. It's as if the universe maintains a cosmic speed limit that no amount of energy can overcome for massive particles. But this isn't a limitation, it's a feature. If massive objects could reach light speed, the universe would become a very different and likely chaotic place. Consider what would happen if you could accelerate your car to light speed. From your perspective, the journey to your destination would take no time at all, but from everyone else's perspective, you would appear frozen in time. The radio waves from your favorite station couldn't catch up to you. The light from street lamps would be blue shifted to gamma rays in front of you and red shifted to radio waves behind you. More fundamentally, if information could travel faster than light, causality itself would break down. You could send messages to your own past, creating paradoxes that would make the universe logically inconsistent. The speed limit doesn't just govern motion, it ensures that cause precedes effect, that the past remains fixed, that the future remains open to possibility. The energy cost of approaching light speed also reveals something beautiful about the relationship between matter and spacetime. Every joule of energy you put into accelerating an object curves spacetime a little more around it. At extreme velocities, this curvature becomes significant, creating gravitational effects that further complicate the acceleration process. The object doesn't just become harder to push because of its increased relativistic mass. It begins to curve spacetime around itself in ways that affect the very geometry through which it moves. This creates a kind of cosmic feedback loop. The faster you try to make something go, the more energy it requires, the more it curves spacetime, the more complex the dynamics become. It's as if the universe has multiple, interlocking mechanisms to ensure that the light speed barrier remains inviolate. No single effect prevents massive objects from reaching light speed. Rather, all the effects conspire together to make it impossible. Yet this impossibility isn't a cosmic cruelty. It's what makes complexity and life possible. If massive objects could easily reach light speed, the universe would be a very different place. Stars might not have stable nuclear fusion, because the particles involved might escape at light speed before complex reactions could occur. Chemistry might be impossible, because atoms and molecules might not be able to maintain their structure. Biology certainly couldn't exist, because the delicate molecular machines that enable life depend on particles having manageable sublight speeds. The cost of acceleration thus reveals itself as one of the universe's most elegant design features. It ensures that information travels at a finite, predictable speed. It guarantees that massive objects can form stable structures. It prevents paradoxes that would make causality meaningless, and it creates a universe where complexity can emerge gradually, where structures can build upon other structures, where the patient dance of chemistry can eventually give rise to the miracle of consciousness contemplating its own existence. In trying to reach the unreachable speed of light, we discover not limitation but liberation. Liberation from paradox, from chaos, from a universe where nothing could build upon anything else because everything would be racing away at the speed of light. The cost of acceleration is the price we pay for living in a cosmos where stories can be told, where causes lead to effects, where the future remains unwritten and full of possibility. Chapter 7. Time slows down as you speed up. Time has always been our most personal possession. The one thing we experience moment by moment, heartbeat by heartbeat, thought by thought. We wake up to it, live through it, and eventually surrender to it. Yet, Einstein revealed that this most intimate aspect of our existence isn't fixed or absolute. It's flexible, malleable, dependent on how fast we're moving through space. The faster you go, the slower time passes for you relative to everyone else. It's not just a theoretical curiosity, it's a fundamental feature of reality that reveals itself every time something approaches the cosmic speed limit. Imagine boarding a spacecraft capable of traveling at 90% the speed of light. As you accelerate away from Earth on a journey to a nearby star, something extraordinary happens to time itself. Your watch continues ticking normally from your perspective, second by second, minute by minute, exactly as it always has. But to observers on Earth watching your departure, your watch appears to be running in slow motion, ticking at roughly half its normal rate. You're aging more slowly, thinking more slowly, existing more slowly than those you left behind. But here's the truly mind-bending part. You don't feel any different. Your thoughts flow normally, your heart beats at its usual rhythm, your body functions exactly as it always has. Time dilation isn't something you experience personally. It's something that happens to you relative to other reference frames. From your perspective, it's everyone else whose clocks have mysteriously sped up, whose lives are racing past in fast forward while you continue at your normal pace. This isn't science fiction or philosophical speculation. Time dilation is measured routinely in particle accelerators where subatomic particles traveling at nearly light speed live significantly longer than their stationary counterparts. Muons created in cosmic ray showers high in the atmosphere should decay long before reaching Earth's surface. But because they're traveling at relativistic speeds, time passes more slowly for them, allowing them to survive their journey through our atmosphere. They arrive at the surface as living proof that time is not absolute. The mathematics of time dilation follow an elegant pattern described by the Lorentz factor. At everyday speeds, the effect is negligible. Traveling at 60 miles per hour in your car causes your clocks to run slow by less than 0.01%. But as velocities approach light speed, the effect becomes dramatic. At 99% light speed, time passes about 7 times more slowly. At 99.9%, it's more than 20 times slower. At 99.99%, it's over 70 times slower. The curve rises sharply, approaching infinity as velocity approaches exactly light speed. This relationship reveals something profound about the structure of spacetime. We tend to think of space and time as separate dimensions, length, width, height, and then time as something entirely different. But Einstein showed us that they're intimately connected aspects of a single four-dimensional fabric. Every object moves through this space-time at exactly light speed, but that motion can be divided between spatial movement and temporal movement in different proportions. When you're sitting still relative to your surroundings, nearly all of your motion through space-time is motion through time. You're racing into the future at close to light speed. When you start moving through space, some of that temporal motion gets converted into spatial motion. The total remains constant at light speed, but the distribution changes. Move faster through space, and you automatically move slower through time. It's like walking northeast instead of due north. Your total walking speed remains the same, but less of it is directed northward. This trade-off between spatial and temporal motion explains why nothing with mass can reach light speed. At exactly light speed, all of your space-time motion would be through space, with none left over for motion through time. Time would stop completely from the perspective of outside observers. You would exist in a state of temporal suspension, experiencing neither change nor the passage of moments. But achieving this state would require infinite energy, making it impossible for anything with mass to reach. The practical implications of time dilation become apparent when we consider interstellar travel. A journey to Proxima Centauri, our nearest stellar neighbor at 4.24 light-years away, would take over 4 years each way at light speed. But for travelers moving at 99% light speed, the subjective journey time would be only about 7 months each way due to time dilation. They could visit nearby stars and return to Earth having aged only a few years, while decades or centuries would have passed for those they left behind. This creates what's known as the twin paradox, a thought experiment where one twin travels to distant stars at nearly light speed, while the other remains on Earth. When the traveling twin returns, they find their Earth-bound sibling has aged much more than they have. The traveler might return after what feels like a few years to find that decades have passed on Earth, that their twin has grown old, that the world has changed beyond recognition. Time dilation makes time travel to the future possible, but it's a one-way journey with no return ticket to the past. But time dilation reveals something even more fundamental about the nature of simultaneity. Events that appear simultaneous to one observer might not be simultaneous to another observer, moving at a different velocity. The faster you're moving relative to someone else, the more your definitions of now begin to diverge. This relativity of simultaneity means that there's no universal now that extends across the entire universe. Each observer carries their own personal definition of the present moment. Consider watching a distant supernova explosion through a telescope from your perspective on Earth. You see the star explode at a specific moment, but an observer traveling toward that star at high speed would see the explosion happen earlier in their reference frame, while an observer traveling away would see it happen later. The explosion itself is a single event in spacetime, but when different observers consider it to happen depends on their motion relative to the star. This flexibility of time has profound implications for how we understand causality and the flow of events. In our everyday experience, we think of time as a river flowing in one direction, carrying all events along with it in a universal sequence. But relativity reveals time as more like a landscape that different observers navigate along different paths. Each path through this temporal landscape is equally valid. Each observer's experience of duration and simultaneity equally real. The slowing of time at high speeds also connects intimately with the equivalence of mass and energy. As an object accelerates, the energy pumped into increasing its speed contributes to its total energy, which appears as increased relativistic mass to outside observers. This increased mass affects the gravitational field around the object, and its inertial resistance to further acceleration. Time dilation, length contraction, and mass increase are all aspects of the same underlying phenomenon, the way space-time responds to motion. GPS satellites, orbiting Earth, provide an everyday example of time dilation in action. These satellites travel at about 14,000 kilometers per hour relative to Earth's surface, causing their onboard clocks to run slightly slower than identical clocks on the ground. The effect is tiny, about 7 microseconds per day, but without correcting for this relativistic time dilation, GPS systems would accumulate errors of several kilometers within hours. Every time you use GPS navigation, you're relying on corrections for Einstein's time dilation effect. Perhaps most remarkably, time dilation suggests that the experience of time isn't fundamental to consciousness or existence. It's contingent on motion through spacetime, the rate at which we experience life, the speed at which our thoughts unfold, the tempo of our biologically processes. All of these are relative to our motion through space. There's no absolute biological clock, no universal rate at which consciousness must operate. Time dilation implies that awareness itself is flexible, capable of operating at different rates depending on the observer's motion through spacetime. In understanding how time slows down as speed increases, we glimpse one of the universe's most profound truths. Time isn't the fixed backdrop against which events unfold, but rather a dimension that can stretch and compress, speed up and slow down depending on motion and gravity. This flexibility of time doesn't make it less real. It makes it more interesting, more connected to the physical processes of the universe, more intimately woven into the fabric of existence itself. And as we approach the cosmic speed limit, we discover that time doesn't just slow down. It reveals its true nature as an integral part of the four-dimensional stage on which the entire drama of existence plays out.
Chapter 8. The Illusion of Simultaneity.
There's something deeply human about the word now. It represents the razor's edge between past and future, the singular moment we inhabit, the shared present that connects us to everyone and everything else in the universe. We schedule meetings for the same time, celebrate New Year's together, observe moments of silence simultaneously, The entire structure of human society depends on our ability to agree on when things happen. But Einstein's relativity shatters this comfortable assumption, revealing that now is not universal. It's personal, dependent on how fast you're moving and where you are in space-time. Imagine you're standing on a train platform watching an express train race past at incredible speed. In one car, you see a passenger at the front of the train turn on a flashlight, while simultaneously, from your perspective, a passenger at the rear turns on their flashlight. To you, these events happen at exactly the same time. You witness them occurring in the same moment, in the same slice of now. But step onto that speeding train, and reality shifts. From the perspective of someone aboard the train, the passenger at the front turned on their flashlight first, followed a fraction of a second later by the passenger at the rear. The same two events that appeared simultaneous to you on the platform occur in sequence to someone moving with the train. Who's right? The answer is both, and neither. Simultaneity isn't an absolute property of events, but a relative judgment that depends on the observer's motion through space-time. This relativity of simultaneity strikes at the heart of our intuitive understanding of time. We naturally assume that if two events happen at the same time, they happen at the same time for everyone, everywhere. It seems obvious that simultaneity should be universal, that the present moment should extend like a cosmic slice through all of space, connecting every point in the universe in a shared now. But the universe doesn't organize itself according to our intuitions. The breakdown of absolute simultaneity emerges directly from the constancy of light speed, because light travels at the same speed for all observers regardless of their motion, and because simultaneity judgments often depend on when light signals from distant events reach us. Different observers in relative motion will disagree about when distant events occurred. It's not that their clocks are wrong or their measurements are flawed, it's that simultaneity itself is observer-dependent. Consider a more dramatic example. Imagine two supernovas exploding in distant galaxies, one in the constellation Orion and another in Cassiopeia. An astronomer on Earth observes both explosions appearing in their telescope at exactly the same moment, a cosmic coincidence that occurs once in billions of years. The explosions seem perfectly simultaneous from Earth's perspective, but now imagine an alien astronomer aboard a spacecraft, traveling at half the speed of light toward Orion. From their perspective, the Orion supernova happened first, followed hours later by the Cassiopeia explosion. Meanwhile, another alien traveling at half-light speed toward Cassiopeia would observe the reverse. Cassiopeia exploded first, then Orion. Three different observers, three different sequences of the same events, all equally valid descriptions of reality. This might seem like mere philosophical wordplay, but it has profound practical consequences. The relativity of simultaneity means there's no universal now that extends across space. Each observer carries their own definition of the present moment, their own way of slicing four-dimensional space-time into three-dimensional spatial snapshots at different times. These slices tilt relative to each other depending on the observer's relative motion, like books leaning at different angles on a shelf. The faster two observers are moving relative to each other, the more their definitions of simultaneity diverge. At everyday speeds, the effect is negligible. You and a friend driving past each other at highway speeds will disagree about simultaneity by less than a nanosecond over distances of thousands of miles. But as relative velocities approach light speed, the disagreements become dramatic, potentially spanning years or centuries for events separated by large distances. This has startling implications for our understanding of free will and determinism. If there's no universal now, then the distinction between past, present, and future becomes observer-dependent. Events that lie in your future might already be in the past for an observer moving rapidly relative to you. From their perspective, your future actions have already occurred. They exist somewhere in the tilted slice of space-time they call now. Does this mean free will is an illusion? Not necessarily, but it does suggest that our everyday concepts of temporal flow and becoming need revision. The universe doesn't unfold moment by moment according to some cosmic clock. Instead, all events, past, present, and future from any given perspective exist equally in the four-dimensional structure of space-time. We experience them sequentially as we move through time, but the sequence depends on our path through space-time. Consider the implications for communication across cosmic distances. If you send a radio message to a friend on a planet orbiting Proxima Centauri, that signal travels at light speed and takes over 4 years to arrive. But simultaneity is relative. From the perspective of an observer traveling rapidly between Earth and Proxima Centauri, your transmission and your friend's reception might not be simultaneous with events that you consider simultaneous on Earth. The very notion of cosmic communication happening in real time becomes meaningless. This relativity of simultaneity also explains why faster-than-light communication would violate causality. If you could send a message faster than light to a distant location, and if an observer there could send a faster-than-light reply, the combination of these superluminal messages, with the relativity of simultaneity, could result in the reply arriving before the original message was sent. You could receive an answer before asking the question, creating paradoxes that would make the logical structure of the universe impossible to maintain. The speed of light thus serves not just as a speed limit for matter and energy, but as the fundamental rate at which causality can propagate. It's the speed at which cause and effect can spread through spacetime, ensuring that events can influence other events only in their future light cone, the region of spacetime that light signals can reach from any given event. This causal structure is what allows the universe to maintain logical consistency despite the relativity of simultaneity. Even more remarkably, the breakdown of absolute simultaneity reveals something profound about the nature of existence itself. In Newton's universe, reality consisted of objects moving through absolute space. According to absolute time, events happened when they happened, period. But Einstein's universe is far richer and stranger. Reality consists of events in space-time, and the temporal relationships between these events depend on the observer's motion through the four-dimensional continuum. This doesn't make reality less real, it makes it more complex and interconnected. Every event in space-time is related to every other event through causal connections that respect the speed of light limit. The past light cone of any event contains all the events that could have influenced it. The future light cone contains all the events it could potentially influence. Between these cones lies a region of events that are space-like, separated from the original event, neither in its past nor its future, but in its elsewhere. Events in this elsewhere region can be simultaneous with the original event from some reference frame, but not from others. They're causally disconnected. They can't influence each other because any signal between them would have to travel faster than light. This causal structure gives spacetime its distinctive geometry, different from the Euclidean geometry of everyday space, with light cones defining the boundaries between past, future, and elsewhere. In practical terms, the relativity of simultaneity affects any technology that depends on precise timing across large distances. The global positioning system, for instance, must account not only for time dilation effects, but also for the fact that simultaneity is observer-dependent. The satellites, ground stations, and GPS receivers are all in relative motion, so their definitions of now don't perfectly align. The system works because these relativistic effects are precisely calculated and corrected. Perhaps most philosophically challenging is what the relativity of simultaneity implies about the nature of time itself. In our everyday experience, time seems to flow like a river, carrying us from past through present into future. But if simultaneity is relative, if different observers slice space-time into different sequences of now, then perhaps time doesn't really flow at all. Perhaps all moments exist equally in the four-dimensional block of space-time, and our sense of temporal passage is just how consciousness navigates through this eternal landscape. This view, known as eternalism or the block universe theory, suggests that all of history, every moment that ever was or will be, exists simultaneously in space-time. The passage of time becomes not a fundamental feature of the universe, but rather how awareness moves through the static four-dimensional structure. Past, present, and future are equally real, equally existent, distinguished only by their location along our particular world line through space-time. The illusion of simultaneity thus opens a window into the deepest mysteries of existence. In revealing that now is not universal, relativity forces us to reconsider our most basic assumptions about time, causality, and reality itself. The speed of light emerges not just as a cosmic speed limit, but as the fundamental constant that defines the causal structure of space-time, ensuring that the universe maintains logical consistency while allowing for the rich complexity of multiple, equally valid perspectives on the flow of time. Chapter 9. Causality and the Cosmic Speed Limit. In the theatre of existence, every play needs rules. Without them, stories become impossible. Heroes could defeat villains before battles begin. Effects could precede their causes. Consequences could occur without actions to trigger them. The universe faces the same challenge on a cosmic scale. How do you maintain a coherent narrative across space and time? How do you ensure that cause precedes effect, that actions lead to consequences, that the story of reality can unfold in a way that makes sense? The answer lies in the cosmic speed limit, the maximum rate at which cause and effect can propagate through space-time. Imagine you could send a message faster than light. At first glance, this seems like it would merely be incredibly useful. Instant communication across interstellar distances, real-time conversations with astronauts on Mars, immediate updates from robotic probes exploring the outer solar system. But dig deeper into the implications, and you discover something disturbing. Faster-than-light communication would shatter the logical foundation of reality itself. The problem emerges from the relativity of simultaneity we explored earlier. Remember that observers in relative motion disagree about when distant events occur. If you send a faster-than-light message from Earth to Alpha Centauri, an observer traveling at high speed between these locations might witness your message arriving before you sent it, an effect that becomes more pronounced the faster the message travels, and the greater the distance it covers. Now imagine your friend on Alpha Centauri receives your faster-than-light message and immediately sends a faster-than-light reply. From their perspective, they're responding after receiving your message, a sensible sequence of cause and effect. But from the perspective of that high-speed observer, both the reply and the original message might arrive on Earth before you sent the original message. You could receive an answer before asking the question, a response before making a statement, an effect before its cause. This isn't just philosophically troubling, it's logically impossible. If effects can precede their causes, then the entire notion of causality becomes meaningless. You could prevent your parents from meeting by sending information to the past, creating paradoxes that would make the existence of the universe itself problematic. The speed of light doesn't just limit how fast things can move, it preserves the rational structure of reality. But causality protection runs deeper than just preventing grandfather paradoxes. The speed of light limit ensures that the universe can maintain a consistent story about itself. Every event in spacetime has what physicists call a light cone, a boundary that defines which other events it can influence and which events can influence it. Nothing can send signals or exert influence outside its light cone, because doing so would require faster-than-light communication. This creates a beautiful structure in spacetime, where every event is causally connected only to events in its future light cone, and causally influenced only by events in its past light cone. Between these cones lies a region of space-like separated events that are causally disconnected. They exist in the events elsewhere, unable to influence it and unable to be influenced by it. This causal structure gives spacetime its distinctive geometry, different from ordinary space, with the speed of light serving as the conversion factor between space and time dimensions. The cosmic speed limit thus acts like a cosmic constitution, establishing the fundamental laws that govern how events can relate to each other. Just as a legal constitution prevents arbitrary exercises of power by establishing clear procedures and limitations, the light speed limit prevents arbitrary violations of causality by establishing clear boundaries on how quickly influence can propagate. Consider what would happen without this speed limit. In a universe where information could travel at infinite speed, every event would be immediately causally connected to every other event. The explosion of a star in a distant galaxy would instantly influence conditions on Earth. The formation of planets around other stars would immediately affect the chemistry of our solar system. The universe would become a single, instantaneously connected system where local independence becomes impossible. Such a universe might seem more efficient, more connected, but it would actually be far less interesting. The gradual propagation of influence at light speed is what allows complexity to emerge locally before being influenced by distant events. It's what permits the formation of stable structures like atoms, molecules, stars, and planets. It's what allows chemistry to proceed without immediate interference from every other chemical reaction in the universe. It's what makes biology possible by creating isolated regions where delicate molecular processes can unfold without being instantly disrupted by cosmic events. The speed limit also creates what we might call causal democracy. No event gets special priority in influencing others. All influences must queue up and propagate at the same maximum speed. A supernova explosion, despite its incredible energy, can't force its influence to travel faster than the gentle light from a firefly. Both must respect the same cosmic speed limit, ensuring that the universe maintains fairness in how quickly different events can affect each other. This democratic aspect of the speed limit has profound implications for the development of intelligence and consciousness. If faster-than-light communication were possible, advanced civilizations might be able to exert instantaneous influence across vast regions of space, potentially preventing the emergence of other forms of consciousness. The light speed limit creates what we might call causal privacy. Regions of spacetime where local events can unfold without immediate interference from distant civilizations or cosmic phenomena. Even more remarkably, the speed limit creates temporal privacy as well. Because simultaneity is relative, and because no influence can propagate faster than light, there's no universal now that would allow one part of the universe to instantly know what's happening everywhere else. Each region of space carries its own local definition of the present moment, its own slice through space-time, its own private experience of the flow of time. This temporal privacy is what makes free will possible, if it exists at all. In a universe with instantaneous communication, the future might be completely determined by the totality of present conditions everywhere. But the light speed limit creates causal horizons, boundaries beyond which events can't immediately influence each other. Your decisions right now can't be instantly determined by events happening simultaneously in distant galaxies, because those events are outside your current light cone. The protection of causality also extends to the quantum realm, where particles can be entangled in ways that seem to violate the spirit, if not the letter, of the cosmic speed limit. When you measure the spin of one entangled particle, you instantly know the spin of its partner, regardless of how far apart they are. This appears to involve faster-than-light communication. But closer examination reveals that no information actually travels between the particles. The correlation is real, but it can't be used to send messages or violate causality. This quantum entanglement pushes right up against the boundaries of what the cosmic speed limit allows, creating correlations without communication, connections without causal influence. It's as if the universe found a way to create relationship without violating the fundamental rule that information cannot travel faster than light. The speed limit remains intact. Causality is preserved, but the universe is revealed to be even stranger and more interconnected than we initially imagined. In particle accelerators, we see causality protection in action every day. When high-energy particles collide, they create showers of new particles that stream away at various speeds. But no matter how energetic the collision, no matter how exotic the particles produced, none of them carry information faster than light. The fastest particles travel at light speed itself. The photons and other massless particles that define the cosmic speed limit. Everything else, no matter how much energy it carries, arrives late. This consistent respect for the speed limit across all physical phenomena suggests something profound about the nature of reality. The cosmic speed limit isn't just a law that particles happen to obey. It's built into the very structure of spacetime itself. It's what allows the universe to have a coherent causal structure, what permits complexity to emerge gradually, what makes stories possible by ensuring that causes precede effects, and that the past remains fixed while the future stays open. Without the cosmic speed limit, the universe would be a very different place, perhaps an impossible place. Causality would break down, paradoxes would proliferate, and the logical structure that allows for the existence of stable patterns, complex chemistry, and conscious observers would collapse. The speed of light thus emerges not as an arbitrary restriction, but as one of the universe's most essential features, the guardian of rationality in a cosmos that might otherwise descend into logical chaos. In protecting causality, the cosmic speed limit protects the very possibility of existence making sense. It ensures that the universe can tell a coherent story about itself, that events can build upon previous events, that complexity can emerge through gradual processes rather than instantaneous chaos. It makes time travel to the past impossible, while keeping the future open to possibility. And in doing so, it creates the conditions necessary for beings like us to exist, to wonder, and to gradually uncover the elegant logical structure that makes our existence possible in the first place. Chapter 10. No pushing past the limit. Why even the most energetic particles in the universe stop short of light speed. Picture yourself standing at the edge of an invisible wall, one that stretches across the entire universe, holding back everything that moves. You can't see it, can't touch it, but it's there, as real as the ground beneath your feet. This wall isn't made of matter or energy. It's made of something far more fundamental. It's made of the very fabric of space and time itself. Even now, as you listen to these words, particles are racing through your body at nearly unimaginable speeds. Cosmic rays, fragments of distant stars that died millions of years ago, are streaming through you like ghostly messengers from the deep universe. Some of these particles carry more energy than a fastball thrown by a major league pitcher, all packed into something smaller than an atom. They've been accelerating through space for eons, gathering speed as they fall through the gravity wells of galaxies, and yet, they never quite reach that ultimate speed. They approach it, like a runner approaching a finish line that keeps moving just slightly ahead of them, but they never cross it. Why is this? What is it about light speed that makes it so untouchable? The answer lies in something that sounds almost like magic, but is actually one of the most precisely measured truths in all of science. As anything with mass moves faster and faster, something extraordinary begins to happen. The faster it goes, the heavier it becomes. Not heavier in the way you'd feel if you gained weight, but heavier in a more fundamental sense. Its mass, its resistance to being pushed, literally increases. Imagine trying to push a shopping cart that becomes more and more loaded with invisible cargo. The faster you try to make it go. At first, it's easy. A gentle push sends it rolling. But as it picks up speed, it's as if the universe itself starts filling that cart with lead weights. Push harder, and more weight appears. The cart becomes more stubborn, more resistant to your efforts. This isn't just a metaphor. It's exactly what happens to every particle, every atom, every speck of matter in the universe. A cosmic ray particle racing at 99% of light speed has become thousands of times more massive than when it started its journey. At 99.9% of light speed, it's tens of thousands of times more massive. And here's the beautiful, impossible thing. To push it that final fraction of a percent to actual light speed would require infinite energy. Not just a lot of energy. Infinite energy. The universe has built itself a perfect lock, and there's no key. But what about light itself? How does light manage to travel at light speed when nothing else can? The answer is as elegant as it is profound. Light has no mass to begin with. A photon, a particle of light, is massless. It doesn't have to overcome the universe's resistance, because there's nothing there to resist. From the moment it's born, whether in the heart of a star or the filament of a light bulb, it travels at exactly one speed, not faster, not slower, always exactly 299,792,458 meters per second. Light doesn't accelerate to light speed. It simply is light speed. Think of it like this. Imagine the universe as a vast highway with a strict speed limit. Everything with mass is like a car that can approach the speed limit, but never quite reach it. The harder you press the accelerator, the more the car seems to weigh, until eventually no engine in the universe could push it any faster. But light is like pure motion itself. It's not a car driving on the highway. It is the highway. Even in the most extreme environments the universe can create, this rule holds absolute. In the cores of neutron stars, where matter is compressed to densities that would turn a teaspoon into a mountain, in the accretion disks around black holes, where particles spiral inward at tremendous speeds, heated to billions of degrees, in the collision of galaxies, where entire solar systems are flung about like sand grains in a cosmic storm. Even there, even in those titanic displays of energy, nothing with mass ever quite reaches light speed. Scientists have found cosmic ray particles so energetic that a single one carries as much kinetic energy as a well-hit tennis ball. Imagine all that macroscopic energy compressed into something billions of times smaller than the period at the end of this sentence. These particles, called ultra-high-energy cosmic rays, represent nature's most powerful particle accelerators. They make our most advanced machines look like toy catapults by comparison. And still they fall short of light speed. It's as if the universe has a cosmic traffic cop, eternally vigilant, never allowing anyone to break the ultimate speed limit. But this traffic cop isn't arbitrary or cruel. It's actually protecting something far more important than we might first realize. Because if things could travel faster than light, if information could zip around the universe instantaneously, then cause and effect themselves would break down. We could have effects before their causes. Conversations where the reply arrives before the question is asked. The speed limit isn't just a rule about motion. It's a rule about logic itself, about the very possibility of a universe that makes sense, and so the cosmic rays keep racing, falling just short of their ultimate goal. The particles in our most powerful accelerators slam into detectors at 99.99999% of light speed, carrying energies that would have seemed godlike to earlier generations, but never ever crossing that final threshold. They approach it asymptotically, like a mathematical curve that forever approaches a line but never quite touches it. In a way, this makes the universe profoundly fair. No matter how much energy you have, no matter how advanced your technology becomes, no matter how clever your engineering, the speed limit applies to everyone equally. Stars and civilizations may rise and fall, but that invisible wall at the edge of velocity remains, constant and unchanging, a fundamental feature of reality itself. Light alone passes through, not because it's special or privileged, but because it carries no baggage, no mass to slow it down, no substance to resist acceleration. It is pure information, pure change, moving through space at the only speed the universe allows for such things. The wall is there, invisible, but absolute, and somehow, in its very impossibility to cross, it makes the universe itself possible. Chapter 11. The Geometry of Reality. Light speed is the conversion rate between space and time. Close your eyes and imagine holding two currencies in your hands, not dollars and euros, not yen and pounds, but something far more fundamental. In one hand, you hold space, distance, length, the gaps between things. In the other hand, you hold time, duration, moments, the flow from now to then. These seem completely different, don't they? The space is where things happen. Time is when they happen. But what if I told you they're actually the same currency, and the speed of light is simply the exchange rate? This isn't poetry or metaphor, this is the deepest truth. Einstein discovered about our universe. Space and time are not separate things that exist independently. They're two aspects of a single unified fabric, called spacetime. And light speed, that cosmic speed limit we can't break, is actually the conversion rate that tells us how much space equals how much time. Picture a cosmic accountant, sitting at the center of reality, with an enormous ledger. Every time something moves through space, this accountant carefully notes how much time had to be spent to cover that distance. Move 1 meter through space. At light speed, that costs you exactly 1 meter divided by 29,9792, 458 meters per second, which equals about 3.3 nanoseconds of time. The math is precise, unchanging, universal. But here's where it gets beautifully strange. You're always moving through spacetime at exactly light speed. Always. Right now, as you sit still listening to these words, you might think you're not moving at all, but you're actually racing through time at the maximum possible rate. You're spending all your velocity budget on moving forward through time, with none left over for moving through space. When you get up and walk across the room, something remarkable happens. You begin trading some of your motion through time for motion through space. You're still moving through space-time at light speed. That never changes. But now you're dividing that motion between space and time. The faster you move through space, the slower you move through time. It's like a cosmic seesaw, more space, less time, more time, less space. But the total always remains constant. This is why time slows down for travelers moving at high speeds. They're not experiencing some mysterious time dilation effect. They're simply converting their motion through time into motion through space. A twin traveling to a distant star at near light speed arrives younger than their earthbound sibling. Not because of some magical aging process, but because they spent most of their space-time velocity moving through space, instead of time. Light itself represents the extreme case. Photons spend their entire velocity budget on moving through space, which means they don't move through time at all. From a photon's perspective, if we can imagine such a thing, its journey from the surface of the sun to your eye happens instantaneously. 8 minutes pass for us, earthbound observers, but for the photon no time passes whatsoever. It exists in an eternal now, experiencing its entire journey as a single moment. Think of spacetime like a vast, flexible rubber sheet. This isn't just a teaching analogy. Modern physics suggests this is surprisingly close to the literal truth. Mass and energy bend this sheet, creating curves and valleys. What we experience as gravity is simply matter following the most direct path through curved spacetime, like a marble rolling along the surface of a curved bowl. But the speed of light isn't just painted onto this cosmic sheet as some arbitrary rule. It's built into the very geometry of the sheet itself. It's the fundamental ratio that defines how the dimensions of space relate to the dimension of time. In a universe with a different light speed, space and time would have a different relationship. And such a universe might not be able to support the complex structures we call matter, stars, planets, or life. The geometry becomes even more mind-bending when we consider acceleration and gravity. Einstein realized that these are actually the same phenomenon, different faces of space-time curvature. When you feel pressed back into your car seat during acceleration, you're experiencing the same fundamental force that keeps your feet planted on the ground. Both are manifestations of movement through curved spacetime. Near massive objects, spacetime curves more dramatically. Time moves slower in these curved regions, not because of some mysterious effect, but because the geometry of spacetime itself is different there. A clock sitting on the surface of a neutron star would tick noticeably slower than an identical clock floating in empty space. The difference isn't in the clocks. It's in the fundamental structure of spacetime itself. This geometric view of reality helps explain why the speed of light is so special. It's not just the speed that light happens to travel. It's the fundamental ratio that defines how reality is put together. It's the speed at which cause and effect propagate through the universe. It's the speed at which information can flow from one place to another. It's the speed at which now spreads outward from any given point. When physicists write equations describing spacetime, they often set the speed of light equal to 1. This isn't just mathematical convenience. It reflects the deep truth that light speed is the natural unit for measuring the relationship between space and time. 1 second of time equals 29.77 tons in 92,458 meters of space. 1 meter of space equals 3.3 nanoseconds of time. The conversion is precise, universal, and unchanging. In this view, what we call the speed of light might be better thought of as the speed of spacetime itself, the fundamental rate at which reality processes information and change. Light simply happens to travel at this speed because light is pure information, unencumbered by mass, free to move through spacetime at the maximum rate the universe allows. The cosmic accountant's ledger is always balanced. Space and time trade back and forth. But their sum, their total velocity through spacetime, remains constant for everything in the universe. It's a conservation law more fundamental than the conservation of energy or momentum. It's the conservation of existence itself, and the exchange rate never changes, no matter what happens. Supernovas, black hole collisions, the birth and death of galaxies. The fundamental geometry of space-time remains the same. 1 unit of space always equals exactly the same amount of time, multiplied by that cosmic constant we call the speed of light. In the end, the speed of light isn't really about light at all. It's about the architecture of reality itself. Chapter 12. When light isn't instant. Why the sun you see is 8 minutes old, and stars may already be gone. Right now, step outside on a sunny day and feel the warmth on your face. That gentle heat, that golden light touching your skin. It's a ghost from the past. The sunshine you're experiencing began its journey 8 minutes and 20 seconds ago, when it first escaped from the roiling surface of the sun. In those 8 minutes, while that light traveled the 93 million miles between the sun and Earth, you might have eaten breakfast, checked your phone, maybe had a brief conversation with a friend, but the light itself experienced none of that time. For the photon, the journey was instantaneous. This creates something almost magical. You're always seeing the sun as it was 8 minutes ago, not as it is now, but as it was. If, in this very moment, something catastrophic happened to our star, if it suddenly vanished or exploded, you wouldn't know about it for another 8 minutes. The sun could be gone, completely gone, and you'd still see it shining peacefully in the sky, still feel its warmth, still experience a perfectly normal sunny day. right up until that final wave of light arrives, and the sky goes dark. But 8 minutes is nothing compared to the time delays from the rest of the universe. Look up at the night sky, and you're seeing not just distant places, but distant times. That bright star in the handle of the Big Dipper, Alkaid, is showing you light that left its surface 104 years ago, when that light began its journey toward your eyes. The First World War hadn't yet begun. Silent films were the height of entertainment technology. The light you're seeing tonight carries with it the electromagnetic signature of a star, as it was in a completely different era of human history. Betelgeuse, the red giant in Orion's shoulder, appears to us as it was roughly 700 years ago, around the time Marco Polo was traveling the Silk Road. The light reaching us tonight began its journey when most of the world's current cities didn't exist, when the technologies that define our modern life were unimaginable. And here's the haunting part. Betelgeuse is a star near the end of its life. Astronomers know it could explode as a supernova at any time. It might already have exploded centuries ago, and we simply don't know yet because the light carrying that information is still traveling toward us. This isn't a limitation of our instruments or our understanding. It's a fundamental feature of reality itself. Information, whether it's light, radio waves, or any other form of electromagnetic radiation, can only travel so fast. The universe has a built-in delay, a cosmic lag time that means we never see anything as it truly is right now. We see everything as it was. The farther out we look, the deeper into the past we peer. The Andromeda Galaxy, that beautiful spiral visible to the naked eye on clear nights, shows us light that's been traveling for 2.5 million years. We're seeing our nearest galactic neighbor as it was when early humans were first walking upright on the African savanna. The galaxy we observe tonight might look completely different now. It might have different spiral arms, different star formation regions, different everything, but we won't know about any of those changes for millions of years. For the most distant galaxies we can detect with our most powerful telescopes, the lag time stretches back, almost to the beginning of the universe itself. We're seeing these ancient island universes as they were when the cosmos was young, when the first stars were being born, when the universe was smaller, denser, and fundamentally different from what it is today. In a very real sense, our telescopes are time machines, allowing us to witness the childhood of reality itself. But this cosmic delay affects more than just starlight. Every form of information, every type of signal, every way that one part of the universe can communicate with another, is bound by this same speed limit. Radio waves from distant civilizations, if they exist, would carry the same time lag. A message broadcast from a planet orbiting Proxima Centauri would take 4 years to reach us, and our reply would take another 4 years to get back. A simple hello and response would require nearly a decade. This creates profound isolation on cosmic scales. Every star system is essentially alone in the universe, separated not just by distance but by time itself. What's happening right now on a planet 20 light-years away, we won't know about it for 20 years. By the time we see it, it will be ancient history to the beings who experienced it. Even within our own solar system, the speed of light creates noticeable delays. Commands sent to Mars rovers must account for the fact that signals take anywhere from 4 to 24 minutes to cross the gap between Earth and Mars, depending on where the planets are in their orbits. Mission controllers on Earth can't joystick a Mars rover in real time. They have to send instructions and then wait to see what happened, like playing a video game with a built-in delay of several minutes. The light from Jupiter takes about 40 minutes to reach us when the giant planet is at its farthest point from Earth. Neptune, at the edge of the solar system, shows us light that's been traveling for hours. We're seeing our own solar system's outermost planets as they were this morning, this afternoon, hours ago. This temporal displacement isn't just a curious fact about astronomy. It's a reminder of something profound about the nature of reality itself. Now is not a universal concept. There is no cosmic moment that we can point to and say this is happening everywhere in the universe right now. Instead, now is a local phenomenon, a bubble of simultaneity that extends only as far as light can travel in an instant. The universe we observe is therefore not a snapshot of a single moment, but a tapestry woven from many different moments, many different nows, spread out across time. The further we look, the deeper we dig into the past. Every photon that reaches our eyes is a messenger from history, carrying news of distant times and places. And sometimes, tragically, those messengers bring news of things that no longer exist. There are stars in tonight's sky that have already exhausted their nuclear fuel and collapsed into white dwarfs, or neutron stars. There may be entire civilizations that have risen and fallen, while their light was en route to us. The universe we see is haunted by its own past, populated by ghosts of light from things that were, but may no longer be. Yet there's something beautiful in this cosmic delay. It means that light itself becomes a form of immortality. Even after stars die, even after planets crumble and galaxies collide, their light continues to race outward through space, carrying the story of what once was to observers who may not even exist yet. Long after our sun burns out, long after Earth is gone, light from our world will still be traveling through the cosmos, carrying the electromagnetic signature of everything we ever were. In a universe where light isn't instant, every photon becomes a time capsule, and every moment of light becomes eternal. Chapter 13. Black holes and the end of light, where even light can't escape. And what that tells us about gravity. Imagine standing at the edge of a cliff, so steep, so impossibly deep, that even light itself cannot climb back out once it falls over the edge. This isn't a metaphor from a dream. It's a real place that exists in our universe. We call them black holes, but that name barely captures the profound strangeness of what they actually are. Regions where space-time itself has been curved, so dramatically that the very geometry of reality breaks down. To understand how this is possible, we need to think about light in a new way. We've grown comfortable thinking of light as the fastest thing in the universe, the one thing that always travels at the cosmic speed limit. But light, like everything else, is affected by gravity, not because photons have mass. They don't. But because gravity isn't really a force pulling on objects. Gravity is curved spacetime. And light simply follows the straightest possible path through whatever curves it encounters. Picture a marble rolling across a perfectly flat table. It travels in a straight line. Constant speed. Predictable direction. Now imagine that table begins to curve and bend. The marble still tries to follow the straightest path possible. But straight now means something different. As the curves become more dramatic, the marble's path becomes more dramatically bent. The marble isn't being pulled or pushed. It's simply following the geometry of the surface it's traveling on. Light does exactly the same thing as it moves through the curved spacetime around massive objects. Near the sun, light bends slightly, just enough that we can measure the deflection during solar eclipses. Near a neutron star, the bending becomes more pronounced. And near a black hole, the curvature becomes so extreme that light can spiral inward in tightening circles until it vanishes completely. But here's what makes black holes truly extraordinary. There's a boundary around them called the event horizon, where the curvature of spacetime becomes so severe that any path light tries to follow, any direction it tries to travel, leads inward. Not some directions, not most directions, all directions. It's as if space itself has become tilted so dramatically that outward no longer exists as a concept. Imagine trying to climb out of a hill that's not just steep, but tilted past vertical in every direction. No matter which way you try to go, you're going downhill. That's what happens to light at a black hole's event horizon. The geometry of spacetime itself has been warped beyond the point where escape is even geometrically possible. From the outside, watching something fall into a black hole creates one of the most haunting spectacles in physics. As an object approaches the event horizon, something strange happens to the light it emits. The intense gravitational field stretches the wavelengths of that light, shifting it toward the red end of the spectrum. The object appears to slow down, moving more and more sluggishly. As it approaches the point of no return, its light becomes redder and redder, dimmer and dimmer, until it fades away completely. Frozen at the event horizon from our perspective, even though from the object's own perspective it has long since crossed over and been destroyed. This creates a kind of cosmic limbo. From the outside universe's perspective, nothing ever quite seems to cross the event horizon. Everything appears to get stuck there, fading away into redshifted oblivion. But from the perspective of the falling object, the crossing happens in finite time. The object passes through the event horizon and continues inward toward the center, experiencing increasingly intense tidal forces that eventually tear it apart at the subatomic level. The event horizon itself is not a physical surface. There's nothing there to touch or bounce off of. It's purely a geometric boundary in spacetime. A point of no return defined entirely by the curvature of space and time. If you could somehow hover just outside the event horizon of a large black hole, you wouldn't see a black wall or feel a solid barrier. You'd see empty space with such extreme curvature that light rays trying to escape would curve back inward. What happens inside the event horizon remains one of the great mysteries of physics. Our current understanding of spacetime breaks down at the center of a black hole, at what we call the singularity here. All our equations produce infinities, infinite density, infinite curvature, infinite tidal forces. This suggests we don't yet have the complete picture, that our understanding of physics needs to be expanded to handle such extreme conditions. But black holes aren't just cosmic monsters devouring light and matter. They're actually among the most perfectly organized objects in the universe. Despite their terrifying reputation, they follow extremely precise mathematical rules. Their properties are determined by just three characteristics: mass, electric charge, and rotation. Everything else about the object that formed the black hole, what it was made of, how it lived, what its history was, gets erased. Physicists call this the no-hair theorem, because black holes are smooth and featureless, with no distinguishing marks or hair to tell us about their past. Paradoxically, while black holes trap light completely, they can also be among the brightest objects in the universe. As matter spirals inward toward the event horizon, it forms what's called an accretion disk, a swirling, superheated ring of material that glows with incredible intensity. The friction and magnetic forces in these disks heat matter to billions of degrees, creating some of the most energetic phenomena we can observe. The light from these accretion disks can outshine entire galaxies. Some black holes also produce jets, narrow beams of particles and radiation that stream outward at nearly light speed. These jets don't come from inside the event horizon, but from the intense magnetic fields in the swirling matter just outside it. The jets can extend for millions of light years, carrying energy across vast distances and influencing the formation of stars in distant galaxies. Recent observations have even allowed us to see black holes directly, or rather to see their shadows. The Event Horizon Telescope captured images of the supermassive black holes at the centers of our galaxy, and the galaxy M87, showing the dark silhouette of the event horizon surrounded by the brilliant glow of the accretion disk. These images confirmed what our theories predicted: black holes really do create regions of space where light cannot escape. In a strange way, black holes represent both the ultimate victory of gravity over light and the ultimate confirmation of light's special status in the universe. They show us what happens when space-time curvature becomes so extreme that even the cosmic speed limit cannot provide escape velocity. Yet they also demonstrate that the speed of light remains constant and universal. It's not that light slows down inside a black hole. It's that space itself has been curved into shapes that trap even light moving at full cosmic speed. Black holes remind us that the universe contains places where our everyday intuitions about space, time, and motion completely break down. They are the universe's most extreme physics laboratories, where the fundamental laws that govern reality are pushed to their absolute limits, and at those limits, even light itself, that universal constant, that cosmic speed limit, that fundamental feature of spacetime, finally meets something it cannot overcome. They are places where light ends, and an ending teaches us just how profound and mysterious the fabric of reality truly is. There might be vast cosmic voids where galaxies are sparse and space is nearly empty. There might be regions where matter clumped together more densely, creating superclusters of galaxies unlike anything in our visible universe. There might even be regions where the fundamental constants of physics are subtly different, where atoms form differently, where the very rules that govern matter and energy take on alternative values. But here's the truly haunting aspect of the cosmic horizon. It's not fixed. As time passes, our observable universe grows larger. Every year, our sphere of visibility expands by exactly 1 light-year in radius. Light that left distant galaxies billions of years ago finally reaches us, bringing new regions of space into view for the first time. We are constantly seeing farther into space and therefore deeper into the past. Yet there are regions that will always remain beyond our reach. The expansion of space itself is accelerating, driven by something we call dark energy. This acceleration means that distant galaxies are moving away from us faster and faster. Some galaxies that we can see today will eventually disappear from view as they get carried away by expanding space at speeds that exceed light itself. Their light will become so stretched and redshifted that it fades beyond detection. In the far future, billions of years from now, observers on Earth, if Earth still exists, will see a much lonelier universe. Many of the galaxies visible in tonight's sky will have been carried beyond the cosmic horizon by the relentless expansion of space. The universe will appear darker, emptier, more isolated, not because galaxies have died, but because they've been carried beyond the reach of light itself. This creates a kind of cosmic claustrophobia. We are trapped inside a sphere of light, unable to see beyond the boundaries set by the age of the universe and the speed of light. No matter how advanced our technology becomes, no matter how clever our theories, there are regions of space that will remain forever mysterious, forever unknowable. Yet there's also something beautiful about living within this horizon. It means that every night, new light is arriving from previously invisible regions of space. Ancient photons that have been traveling since shortly after the Big Bang are constantly reaching our telescopes, bringing fresh news from the deepest past. We live in a universe that is constantly revealing new secrets, constantly expanding our understanding of what exists beyond our immediate vicinity. The cosmic horizon also creates a profound form of cosmic democracy. Every observer in the universe lives at the center of their own observable sphere. From their perspective, they see the same distance in all directions, bounded by the same fundamental relationship between light speed and cosmic age. A being, on a planet in the Andromeda galaxy, sees their own cosmic horizon, with Earth and the Milky Way near the edge of their observable universe. This means there's no special vantage point in the cosmos, no place where you can see everything that exists. Every observer sees their own piece of the cosmic puzzle, their own sampling of the infinite richness that lies beyond every horizon. The universe reveals itself partially to everyone and completely to no one. Perhaps this is fitting. The cosmos is so vast, so rich, so full of structure and beauty, that no single perspective could encompass it all. We are each granted our own window into infinity, our own sphere of light carrying messages from the depths of space and time. Beyond our horizon lie wonders we will never see, mysteries we will never solve, beauties we will never directly witness. But knowing they exist, knowing that our visible universe is just a small sample of something unimaginably larger, fills our local cosmic neighborhood with deeper meaning. Every galaxy we can see represents billions we cannot. Every star in our night sky stands for countless others beyond the reach of light itself. We live surrounded by infinity, able to see only a small but beautiful portion of what exists. And perhaps that's enough. Perhaps the wonder lies not in seeing everything, but in knowing that everything exists, stretching out beyond every horizon, waiting in the darkness for light that may never reach us. The universe is larger than what we can see, and somehow that makes what we can see even more precious. Chapter 18, Does Light Ever Slow Down? Exploring how light changes speed in glass, water, and gravity. Walk into a swimming pool on a sunny day and something magical happens. The bottom of the pool appears closer than it actually is. Objects underwater seem bent and distorted, and if you've ever tried to grab something submerged, you've discovered that your eyes lie to you about where things really are. This isn't an optical illusion in the usual sense. It's evidence that light itself behaves differently when it travels through different materials. The cosmic speed limit that we've been exploring, 29,792,458 meters per second, applies only to light traveling through the vacuum of empty space. In matter, light slows down. But here's the beautiful paradox. Individual photons never actually change speed. Even when light appears to slow down dramatically in glass or water or diamond, each individual photon still travels at exactly the cosmic speed limit. The apparent slowdown is actually something far more subtle and strange. A kind of cosmic relay race where photons are constantly being absorbed and re-emitted by the atoms they encounter. Picture light entering a piece of glass. The first photon races toward the surface at full light speed and strikes an electron in one of the glass atoms. The electron absorbs the photon's energy, becoming temporarily excited, then quickly re-emits a new photon in the same direction. That new photon travels at full light speed to the next atom where the process repeats. Absorption, excitation, re-emission, over and over, millions of times as the light makes its way through the material. Each individual leg of this atomic relay race happens at full light speed, but the brief delays during absorption and re-emission add up. The light takes a longer path through the material than it would through empty space, even though each photon along the way travels at the cosmic speed limit. It's like a runner who maintains the same sprinting speed but has to stop at every block to hand off the baton to the next runner. Different materials create different delays, leading to what physicists call the refractive index, a number that tells us how much slower light appears to travel in that substance compared to vacuum. Water has a refractive index of about 1.33, meaning light appears to travel about 25% slower in water than in vacuum. Glass can slow light down by 30 to 50%, depending on its composition. Diamond, with its incredibly dense crystal structure, can slow light down to less than half its vacuum speed. But the most extreme slowdowns happen in specially prepared materials called slow light media. In certain ultra-cold atomic gases, researchers have managed to slow light down to just 17 meters per second, slower than a car on a residential street. In the most extreme experiments, they've brought light to a complete stop, storing its information in the quantum states of atoms, then releasing it later to continue its journey at full speed. These aren't just laboratory curiosities. The bending of light as it slows down when entering materials is what makes eyeglasses work, what creates the brilliant colors in cut diamonds, what causes rainbows to form when sunlight passes through water droplets. Every time you look through a window, every time you see your reflection in water, every time light creates beauty by interacting with matter, you're witnessing the consequences of light's apparent slowdown in materials. But there's another way that light can slow down, or at least appear to slow down from our perspective. In the presence of strong gravitational fields, light takes longer to travel between 2 points, not because the photons themselves move slower, but because space and time themselves become curved and stretched. Near a massive object like the Sun, space is curved in such a way that light must follow a longer path than it would in flat space-time. From our perspective, watching from far away, the light appears to slow down as it passes near the Sun, but from the light's own perspective, it's still traveling at exactly the cosmic speed limit through whatever curved space-time it finds itself in. This gravitational effect becomes extreme near black holes. Light trying to escape from near the event horizon becomes increasingly redshifted, its wavelength stretched out by the intense gravitational field. From the perspective of a distant observer, the light appears to slow down dramatically, taking longer and longer to escape as it climbs out of the gravitational well. The photons themselves still move at light speed through the curved spacetime they inhabit, but that spacetime is so distorted that their journey takes much longer than it would in flat space. Time dilation adds another layer of complexity. In a strong gravitational field, time itself runs slower relative to observers in weaker fields. A clock near the surface of a neutron star would tick noticeably slower than an identical clock far away in space. This means that even though light maintains its constant speed relative to local time, that local time is running slow compared to distant observers. The light appears to slow down when viewed from afar, even though it's moving at normal light speed according to local measurements. These effects aren't just theoretical. GPS satellites have to account for the fact that time runs slightly faster in their higher orbits, where Earth's gravitational field is weaker. If we didn't correct for these relativistic effects, GPS would accumulate errors of several miles per day. Every time you use GPS navigation, you're relying on calculations that account for how gravity affects the apparent speed of light and the passage of time. Perhaps the most mind-bending aspect of light's variable speed is what it reveals about the nature of speed itself. When we say that the speed of light is constant, we mean that it's constant relative to the local structure of space-time. Light always travels at the same speed through whatever environment it finds itself in, whether that environment is empty, vacuum, curved space-time near a massive object, or the quantum field of interactions within a material. But environments themselves can vary dramatically. The vacuum of space provides the freeway where light travels at maximum speed. Materials create a more complex environment where light has to interact with matter, creating apparent slowdowns. Curved spacetime, near massive objects, creates longer paths that light must follow, again creating apparent delays from the perspective of distant observers. In every case, though, Light itself never violates the fundamental cosmic speed limit. It always travels at exactly c, the cosmic speed limit, through whatever space-time environment it inhabits. What changes is not the intrinsic speed of light, but the structure of the environment through which it travels. This distinction is crucial for understanding why the cosmic speed limit remains truly fundamental. No information, no influence, no causal effect can travel faster than light speed through any given region of space-time. The apparent slowdowns we observe don't violate this rule. They're consequences of light having to navigate more complex environments or follow longer paths through curved space. Even in the most exotic scenarios physicists can imagine, wormholes, warp drives, extra dimensions, the local speed limit remains intact. Light always travels at light speed through its immediate environment. What might change are the properties of space and time themselves, potentially creating shortcuts or alternate routes that could make distant destinations effectively closer. But in all cases, the fundamental relationship between space, time, and the propagation of information remains governed by that same cosmic constant, 29,792,458 meters per second. It's not just the speed of light, it's the speed of causality itself, the rate at which influence can spread from one point to another in the universe. So when light appears to slow down in glass or water, or near a black hole, it's not really violating the cosmic speed limit. It's showing us that the universe is far more complex and beautiful than a simple vacuum where everything travels in straight lines. It's revealing the rich interplay between light and matter, between energy and space-time, between the fundamental constants that govern reality, and the countless ways those constants can manifest in different environments. Light never truly slows down. But the universe provides countless ways for it to take interesting detours on its eternal journey through space and time. Chapter 19. Why we can't catch a photon. No matter how fast you go, light still outruns you. Or, imagine you're driving down a highway at night, and you decide to race the headlight beams from your car. You press the accelerator, faster and faster, trying to catch up to the light streaming ahead of you into the darkness. Common sense might suggest that if you could somehow reach light speed yourself, you would find yourself traveling alongside your own headlight beams, like running alongside a friend on a track. But the universe has a different plan, one so counterintuitive that it challenged humanity's understanding of reality itself. No matter how fast you go, light always pulls away from you at exactly the same speed, 20,99,792,458 meters per second. This isn't because you're not going fast enough, or because your vehicle isn't powerful enough. It's because the universe operates according to rules that defy our everyday intuition about speed and motion. In our ordinary experience, speeds add together in predictable ways. If you're walking forward at 3 miles per hour on a train moving at 60 miles per hour, your speed relative to the ground is 63 miles per hour. If you throw a ball forward from the train at 20 miles per hour, the ball moves at 80 miles per hour relative to the ground. This is how motion works in the familiar world of cars and trains and thrown objects. But light doesn't follow these rules. If you're traveling at half the speed of light and you shine a flashlight forward, the light from that flashlight still moves away from you at full light speed, not at 1.5 times light speed as our intuition might suggest. This seems impossible, but it's been verified in countless experiments. Light always moves at light speed relative to anyone who measures it, regardless of how fast that person is moving. This strange behavior is a fundamental feature of space-time itself. When you try to catch up to light by moving faster and faster, something remarkable happens to you. Time itself begins to slow down from the perspective of outside observers. Your clocks run slower, your biological processes slow down, even your thoughts occur at a slower rate when viewed from the outside. But from your own perspective, everything seems normal. Your clocks tick at their usual rate, you think at your usual speed, and light still appears to move away from you at exactly light speed. The universe essentially conspires to make light speed the same for everyone. As you approach light speed, time dilation becomes so extreme that even though you're moving incredibly fast through space, light still manages to outrun you by exactly the same margin as when you were standing still. But why can't anything with mass actually reach light speed? The answer lies in something physicists call relativistic mass. As you accelerate toward light speed, you don't just get faster, you also get more massive. This isn't like gaining weight by eating too much. It's a fundamental change in your resistance to further acceleration. The faster you go, the more massive you become, and the more energy it takes to make you go even faster. Picture trying to push a shopping cart that becomes heavier with every step. At first, it's easy to accelerate the cart, but as it speeds up, it seems to fill with invisible lead weights. You push harder, but the cart becomes even more resistant to acceleration. Near light speed, the cart would become so massive that no conceivable force could push it any faster. This is exactly what happens to any object with mass as it approaches light speed. At 90% of light speed, an object has become more than twice as massive as when it was at rest. At 99% of light speed, it's more than 7 times as massive. At 99.9% of light speed, it's more than 22 times as massive. And to reach actual light speed would require the object to become infinitely massive, which would require infinite energy to achieve. The universe has built an insurmountable wall at light speed, one that becomes higher and more impenetrable. The closer you get to it, every step toward light speed requires exponentially more energy than the last. It's like trying to climb a mountain that becomes infinitely steep at its peak. Scientists have pushed particles to incredible speeds in particle accelerators, getting closer and closer to light speed. The Large Hadron Collider can accelerate protons to 99.999999991% of light speed, so close that the difference is almost unimaginable. At this speed, the protons have become about 7,500 times more massive than when they were at rest. But even is all that energy, even with the most powerful machines humans have ever built, we still can't push anything with mass to actual light speed. Light itself achieves light speed not by accelerating to it, but by having no mass to begin with. A photon doesn't start slow and speed up. It emerges from its source already traveling at exactly light speed. It never experiences acceleration, never builds up speed gradually. From the moment of its creation, whether in the heart of a star or the filament of a light bulb, it moves at the cosmic speed limit. This creates a beautiful symmetry in the universe. Everything with mass can approach light speed, but never reach it. Everything without mass, photons, gravitational waves, the hypothetical particles that carry forces, must travel at exactly light speed, and can never go slower. There's no middle ground, no partial light speed for massless particles. They travel at light speed, or they don't exist at all. The impossibility of catching light has profound implications for space travel and communication. It means that no matter how advanced our technology becomes, we will always be limited by the cosmic speed limit. We can build faster and faster spacecraft, but we'll never build one that can outrun its own radio signals or arrive at a destination before light from its departure point. This also means that the universe maintains a fundamental isolation between distant regions. News from other star systems will always take years to reach us, moving at light speed through the void. If there are civilizations on planets orbiting other stars, our conversations with them will always be separated by years-long delays. A simple hello and response to the nearest star system would take nearly a decade. But perhaps there's beauty in this cosmic speed limit. It means that cause and effect maintain their logical relationship. Effects never arrive before their causes. Consequences never precede actions. It creates a universe where information takes time to propagate, where distant events happen in a logical sequence, where the future cannot reach backward to alter the past. The impossibility of catching light also means that light itself serves as a kind of cosmic referee, ensuring that the rules of causality are never violated. No matter how clever we become, no matter what technologies we develop, we cannot send information into our own past, or receive messages from our own future. The speed of light creates a firewall around causality itself. In trying to catch light, we discover something profound about the nature of reality. Some limits are not mere engineering challenges to be overcome, but fundamental features of how the universe operates. The speed of light isn't just fast, it's the speed of time itself, the rate at which cause and effect propagate through reality. We cannot catch light, because light is not separate from the fabric of spacetime. It is an expression of that fabric. To catch light would be to catch up to time itself, to step outside the flow of causality that makes existence possible. Light will always outrun us, not as a limitation on our capabilities, but as a reminder of our place within the beautiful, logical, precisely structured reality we call home. Chapter 20. The cosmic speed limit isn't just for light. Why all information, energy, and influence are bound by Sere. The speed of light isn't really about light at all. This might sound paradoxical, but it's one of the most profound realizations in modern physics. What we call the speed of light is actually something far more fundamental, the maximum speed at which any cause can produce an effect in our universe. It's the cosmic speed limit that governs not just photons racing through space, but every form of information, energy, and influence that exists. To understand this deeper truth, we need to step back from our everyday experience, where causes and effects seem instantaneous. When you flip a light switch, the bulb illuminates immediately. When you push a book off a table, it falls right away. But these apparent instantaneous connections are illusions created by the vast speed of light, compared to the scales we're used to. In reality, every cause must send a signal to produce its effect, and that signal cannot travel faster than approximately 300 million meters per second. Consider gravity, which seems to act instantly across vast distances. When Einstein developed his theory of general relativity, he revealed that gravitational effects actually propagated exactly the speed of light. If the sun suddenly vanished, Earth wouldn't immediately fly off into space. We would continue orbiting for about 8 minutes. The time it takes for the gravitational change to reach us at light speed. The same duration it takes for the sun's light to reach us is exactly how long it takes for the gravitational information to make the journey. This isn't a coincidence. Both phenomena are manifestations of the same underlying principle. Spacetime itself has a fundamental speed limit. Gravity doesn't pull objects together instantly across space. Instead, massive objects curve spacetime, and these curves propagate outward at the maximum possible speed, the speed of light. What we experience as gravitational force is actually the result of objects following the straightest possible paths through curved spacetime. Electromagnetic fields follow the same rule. When you move a magnet, the change in its magnetic field doesn't instantly affect a piece of iron across the room. The electromagnetic disturbance travels outward at light speed, carrying the information about the magnet's new position. Only when this wavefront reaches the iron does it begin to respond. Every electromagnetic phenomenon, from radio waves to X-rays, from the electricity in your house to the magnetic field of Earth itself, operates under this same speed restriction. Even more remarkably, this speed limit applies to information itself. In the quantum realm, particles can become entangled, creating mysterious correlations that seem to violate our intuitions about locality. When you measure one particle in an entangled pair, you instantly know something about its partner, even if that partner is on the other side of the galaxy. But, and this is crucial, no usable information travels faster than light between the particles. The correlations are real, but they cannot be used to send messages or transmit energy faster than the cosmic speed limit allows. This principle has profound implications for the structure of causality itself. The speed of light defines what philosophers call the light cone, the boundary between events that can influence each other and those that cannot. If you're sitting in a chair right now, there are events happening in distant galaxies that cannot possibly affect you yet, because not enough time has passed for light to travel from there to here, since those events occurred. Similarly, your actions right now cannot influence events in those same galaxies until light has time to carry that influence across space. The universality of this speed limit emerges from the geometry of space-time itself. In Einstein's relativity, space and time are woven together into a four-dimensional fabric. The speed of light represents the conversion factor between space and time units. It's built into the very architecture of reality. Just as there's a maximum speed you can travel through space while remaining stationary in time, there's a maximum rate at which any change can propagate through space-time. This geometric understanding helps explain why the speed limit applies to everything, not just light. Photons happen to travel at this maximum speed because they have no mass to slow them down. But the speed itself is a property of space-time, not of light. It's the rate at which the present moment expands outward from any given point, defining the boundary between here and now, and somewhere else, somewhere else. Particles with mass can never reach this speed, because doing so would require infinite energy. As objects accelerate, they gain momentum and energy, but they also experience relativistic effects that make further acceleration increasingly difficult. The faster they go, The more their mass effectively increases, and the more energy is required for each additional increment of speed, the speed of light becomes an asymptotic limit, approachable but never reachable. Yet massless particles like photons must travel at exactly this speed. They cannot slow down or speed up. They exist only at the cosmic speed limit. This reveals something beautiful about the structure of reality. The universe has exactly one speed for objects without mass, and that speed is also the maximum speed at which causality itself can operate. The implications extend beyond physics into philosophy and our understanding of free will, consciousness, and the nature of time. The speed of light defines the rate at which the future becomes the present, becomes the past. It sets the tempo of existence itself, determining how quickly choices can lead to consequences, and how rapidly information can spread through any system. Whether that system is a human brain, a computer, or the entire observable universe. Understanding that the cosmic speed limit applies to all forms of influence helps us appreciate the deep unity underlying seemingly different phenomena, whether we're talking about light waves, gravitational waves, electromagnetic fields, or the propagation of quantum information. We're really talking about different aspects of the same fundamental principle, the maximum rate at which reality can change from one state to another. This speed limit isn't a constraint imposed on the universe from outside. It's an intrinsic feature of the way space and time relate to each other. It's as fundamental as the fact that circles have a constant ratio between circumference and diameter, or that triangles in flat space have angles that sum to 180 degrees. The speed of light is built into the grammar of existence itself. In the next chapter, we'll explore whether there might be ways to circumvent this seemingly absolute limit through exotic physics, like warp drives and wormholes, and discover why the universe's speed limit might be more flexible than it initially appears, even while remaining fundamentally unbreakable. Chapter 21. Warp drives and wormholes. Real or fantasy? Can we cheat the light limit with exotic physics? The cosmic speed limit seems absolute, but human ingenuity has always sought ways around seemingly impossible barriers. Science fiction has long imagined faster-than-light travel through concepts like warp drives, hyperspace jumps, and traversable wormholes. What's remarkable is that some of these seemingly fantastical ideas actually have solid theoretical foundations in modern physics, though the practical challenges are so enormous they may forever remain in the realm of imagination. Let's start with the most famous attempt to circumvent the light barrier, the Alcubierre warp drive. Proposed by physicist Miguel Alcubierre in 1994, this concept doesn't actually move a spacecraft faster than light through space. Instead, it manipulates spacetime itself, contracting space in front of the vehicle and expanding it behind. The ship remains in a bubble of normal spacetime, never locally exceeding the speed of light, while the bubble itself moves faster than light relative to distant observers. Think of it like riding a moving walkway in an airport. You might be walking at normal speed on the walkway itself, but relative to the terminal, you're moving faster than you could walk alone. The Alcubierre drive would create a similar effect with spacetime itself, surfing on a wave of geometric distortion that carries the ship along at superluminal speeds. The mathematics of the Alcubierre drive are surprisingly robust. Einstein's field equations, which describe how matter and energy curve spacetime, do allow for such exotic geometries. The drive doesn't violate relativity because it never accelerates matter through spacetime faster than light. It moves spacetime itself. From the perspective of someone inside the warp bubble, they remain at rest while the universe rushes past them. However, the energy requirements are mind-boggling. Early calculations suggested that creating an Alcubierre drive would require negative energy equivalent to the mass energy of Jupiter. Even with later refinements that reduce these requirements, we're still talking about exotic matter with properties that may not exist in nature. The drive would need substances with negative energy density matter that weighs less than nothing, creating a kind of gravitational repulsion rather than attraction. Negative energy isn't pure fantasy. Quantum mechanics predicts its existence in specific circumstances, such as between the plates in the Casimir effect, where quantum fluctuations create measurable forces. But scaling this up to the quantities needed for a warp drive represents a technological challenge that may be fundamentally impossible. We would need to not just create exotic matter, but manipulate it with precision on cosmic scales. Even if we solve the energy problem, the Alcubierre drive faces other serious challenges. The interior of the warp bubble would be causally disconnected from the outside universe. The occupants couldn't steer the drive or communicate with the outside world during travel. They would be passengers on a predetermined course, unable to navigate or respond to obstacles. Additionally, when the drive finally stopped, it might release a burst of radiation that could sterilize entire star systems. Wormholes present a different approach to faster-than-light travel. These hypothetical tunnels through space-time could connect distant regions of the universe, allowing travelers to take shortcuts through higher dimensions. Einstein and Nathan Rosen first described these structures in 1935, though they initially seemed to exist only as mathematical curiosities, with no physical reality. A wormhole would essentially be a bridge between two black holes, connecting their event horizons through a throat that passes through a higher dimension. If you could somehow travel through this throat, you might emerge in a completely different part of the universe or even a different time, without ever exceeding the speed of light locally. You would be taking a shortcut through the geometry of space-time itself. The challenge with natural wormholes is that they would be incredibly unstable. Any matter or energy entering a wormhole would cause it to collapse faster than anything could traverse it. To keep a wormhole open long enough for travel, you would need to line its throat with exotic matter, having negative energy density, the same problematic substance required for warp drives. Traversable wormholes also raise profound questions about causality and the nature of time. If a wormhole connected two regions of space, and those regions were moving relative to each other at high speeds, time dilation effects could make the wormhole into a time machine. Travelers could potentially return to their starting point before they left, creating paradoxes that might be fundamentally impossible in our universe. String theory suggests other possibilities for circumventing the light speed limit. In some models, our three-dimensional space is embedded in a higher dimensional bulk space, and it might be possible to travel through these extra dimensions. Gravity appears to propagate through all dimensions, which is why it's so much weaker than other forces. It's spreading out through more dimensions than electromagnetism or the nuclear forces, which are confined to our three-dimensional brain. If we could somehow access these extra dimensions, we might be able to take shortcuts similar to wormholes. But the energy scales involved in manipulating extra dimensions are likely to be comparable to those found in black holes, or the moments after the Big Bang. Any technology capable of accessing extra dimensions would represent a level of advancement far beyond anything we can currently imagine. Quantum entanglement offers another tantalizing possibility. When particles become entangled, measuring one instantly affects the other, regardless of the distance between them. This has led some to speculate about quantum communication, or even quantum teleportation systems that could circumvent the light speed limit. However, quantum mechanics places strict limits on what can be accomplished through entanglement. While entangled particles do exhibit instantaneous correlations, these correlations cannot be used to transmit usable information faster than light. The measurement results on one particle appear random until compared with measurements on its entangled partner. No meaningful message can be sent through quantum entanglement alone, though it might serve as a component in more exotic faster-than-light communication schemes. Some physicists have proposed using quantum entanglement in conjunction with wormholes to create quantum wormholes, or EA-EPR bridges, where entanglement, EPR, is equivalent to wormhole connections, Einstein-Rosen bridges. This idea suggests that quantum entanglement might actually create tiny wormhole connections between particles, though these would be far too small and short-lived for macroscopic travel. The search for ways around the light speed limit has also led to investigations of modified theories of gravity and alternative models of spacetime. Some theories propose that space itself might have a granular structure at the smallest scales, like pixels on a cosmic screen. If so, there might be ways to manipulate this granularity to achieve faster-than-light effects, though such ideas remain highly speculative. Despite all these theoretical possibilities, the consensus among physicists is that faster-than-light travel faces obstacles that may be truly insurmountable. The exotic matter required for warp drives and stable wormholes might not exist in sufficient quantities. The energy requirements might be fundamentally impossible to meet, and the causality paradoxes that arise from faster-than-light travel might represent logical contradictions that nature simply doesn't allow. Yet the very fact that these concepts have mathematical foundations in our best theories of physics suggests that the universe might be stranger and more flexible than we imagine. Even if faster-than-light travel proves impossible, The investigation of these ideas has deepened our understanding of spacetime, causality, and the fundamental structure of reality. Whether they remain forever in the realm of science fiction, or eventually become engineering challenges for future civilizations, warp drives and wormholes represent the boundary between what we know is impossible and what we dare to dream might be possible. Chapter 22. When Science Fiction Gets It Wrong. Common myths about light speed in movies and books. Science fiction has given us some of the most memorable imagery in popular culture, from the Enterprise's warp speed to the Millennium Falcon jumping to hyperspace. These stories have inspired generations of scientists and engineers, but they've also created persistent misconceptions about the speed of light and the nature of space travel. Understanding where science fiction gets it wrong, and occasionally right, helps us appreciate both the creativity of storytellers and the genuine strangeness of relativistic physics. The most common misconception in science fiction is the idea that faster-than-light travel is simply a matter of building a more powerful engine. In countless movies and TV shows, spaceships accelerate smoothly through light speed as if it were just another velocity barrier, like breaking the sound barrier. The ship's speedometer reads warp 1, warp 2, and so on, suggesting that light speed is merely a stepping stone to even greater velocities. This portrayal fundamentally misunderstands the nature of the light speed limit. Unlike the sound barrier, which can be exceeded by applying enough force, the speed of light represents an asymptotic limit that becomes exponentially more difficult to approach. As objects with mass accelerate toward light speed, their energy requirements grow without bound. No amount of fuel or engine power can push a massive object past this barrier. The mathematics of relativity forbid it. Absolutely. The visual representation of faster-than-light travel in movies creates another layer of misconceptions. Star Trek's familiar warp streaks show stars stretching into lines as the Enterprise accelerates, while Star Wars' hyperspace jumps display similar effects. These dramatic visuals suggest that faster-than-light travel involves some kind of passage through normal space at incredible velocities, but they ignore the fundamental problems this would create. If a spacecraft were actually moving faster than light through normal space, the crew wouldn't see streaking stars. Light from stars ahead would be blue shifted to such extreme frequencies it would become deadly radiation, while light from stars behind wouldn't be able to catch up to the ship at all. The view outside would likely be a sphere of intense blue-white light ahead, and complete darkness behind. The beautiful star field effects that make for compelling cinema bear no resemblance to what faster-than-light travel would actually look like if it were possible at all. Many science fiction stories also ignore the time dilation effects that occur at relativistic speeds. Characters routinely travel at significant fractions of light speed without aging differently than people back on Earth. In reality, time dilation becomes noticeable at speeds above about 10% of light speed, and grows increasingly dramatic as you approach the light barrier. The journey at 90% of light speed, that takes 1 year from the traveler's perspective, would consume over 2 years of Earth time. This oversight creates logical problems in science fiction narratives. If characters can travel between star systems in weeks or months of their subjective time, decades or centuries should be passing on their home worlds. Civilizations should rise and fall, while the heroes are in transit. The dramatic tension of racing against time becomes meaningless when time itself behaves so differently for travelers versus those left behind. The treatment of communication in science fiction reveals another fundamental misunderstanding. In many stories, characters maintain real-time conversations with people light years away, as if distance poses no barrier to instantaneous communication. Radio signals in these fictional universes apparently travel faster than light, allowing for dramatic scenes where characters coordinate battles across vast distances or receive urgent warnings just in time. In reality, a radio conversation with someone on Mars would involve delays of between 4 and 24 minutes depending on the planet's relative positions. A phone call to the nearest star would require over 8 years between question and response. Interstellar civilizations could never maintain the kind of centralized coordination we see in most science fiction. News, orders, and information would propagate through space at the speed of light, creating inevitable delays that would fragment any galactic empire into independent regions operating on their own timescales. Science fiction often treats energy and momentum as if they work differently at relativistic speeds. Spaceships fire lasers and launch missiles while traveling faster than light, apparently unaware that the energy dynamics of such actions would be completely different from normal experience. A photon torpedo fired forward from a ship traveling faster than light would actually be traveling backward relative to normal space, while one fired backward would be moving forward at incredible speeds. The depiction of space battles in science fiction movies creates particularly egregious violations of relativistic physics. Ships maneuver like World War II fighters, banking and turning as if they were flying through an atmosphere. They fire weapons that travel slowly enough for audiences to track with their eyes, when real space weapons would either be lasers moving at light speed, or projectiles whose relativistic effects would make them devastatingly powerful. Perhaps most problematically, science fiction often ignores the fundamental relationship between energy and mass, revealed by Einstein's famous equation E=mc². The energy required to accelerate even a small spacecraft to relativistic speeds would dwarf the total energy output of modern civilization. Yet fictional spaceships routinely carry enough fuel to make multiple faster-than-light jumps, as if the energy requirements were merely an engineering challenge rather than a fundamental physical limitation. Some science fiction does make honest attempts to grapple with relativistic physics. Kim Stanley Robinson's novels often incorporate realistic treatments of time dilation and the enormous energy requirements of interstellar travel. Alastair Reynolds, a former astrophysicist, creates stories where light speed limits constrain the development of human civilization across multiple star systems. These works demonstrate that scientific accuracy can enhance, rather than diminish, dramatic storytelling. The generation ship concept represents one of science fiction's more realistic approaches to interstellar travel. Rather than circumventing the light speed limit, these stories accept it and explore the social and psychological challenges of journeys lasting centuries or millennia. The constraints imposed by realistic physics create new forms of drama and conflict that purely fantastical faster-than-light stories cannot achieve. Occasionally, science fiction anticipates real scientific developments. The communication delays in science fiction stories sometimes lead to plot devices that mirror real proposals for interstellar communication networks. The idea of using gravitational effects to accelerate spacecraft appears in both fiction and serious scientific research. Some fictional faster-than-light drives bear resemblance to theoretical concepts like the Alcubierre warp drive, though usually without the crushing practical limitations that make such devices effectively impossible. The persistence of these misconceptions in popular culture matters because they shape public understanding of physics and space exploration. When audiences expect faster-than-light travel to be simply a matter of better engineering, they may underestimate the profound challenges facing real space exploration. When they assume that communication across interstellar distances is instantaneous, they fail to appreciate the isolation that would characterize any genuine interstellar civilization. Yet, science fiction serves crucial purposes that justify its occasional departures from physical reality. These stories inspire scientific careers, explore the implications of technological advancement, and examine fundamental questions about human nature and our place in the universe. The best science fiction uses its violations of known physics as tools for exploring deeper truths about consciousness, society, and the meaning of existence. The key is recognizing the difference between scientific accuracy and storytelling necessity. Science fiction at its best acknowledges the constraints of physical law while finding creative ways to work within or around them. It uses violations of physics not as casual conveniences, but as opportunities to explore what might be possible at the very boundaries of scientific knowledge. Understanding where science fiction gets the speed of light wrong helps us appreciate both the genuine insights of these stories and the remarkable strangeness of the real universe. The actual physics of light speed and relativity is often far more bizarre and wonderful than anything fiction has imagined. A universe where time dilates, space contracts, and the fastest possible speed is also the speed at which massless particles must travel. Reality, as always, proves more creative than any storyteller. Chapter 23. Could light have been slower in the past? Exploring theories of variable light speed in early cosmology. One of the most fundamental assumptions in physics is that the speed of light has remained constant throughout the history of the universe. This assumption underlies our understanding of cosmic distances, the age of the universe, and the evolution of fundamental forces. But what if this assumption is wrong? What if the speed of light has changed over cosmic time, and the universe's most sacred constant is actually variable? This question isn't merely philosophical speculation. Several serious theoretical frameworks suggest that fundamental constants of physics, including the speed of light, might have evolved as the universe aged. These variable speed of light (VSL) theories propose that c, the cosmic speed limit, could have been dramatically different in the early universe, with profound implications for cosmology, particle physics, and our understanding of reality itself. The idea first gained serious attention in the late 1990s when physicists João Magejo and Andreas Albrecht proposed VSL cosmology as an alternative to cosmic inflation. Standard Big Bang cosmology faces several puzzles. Why is the universe so uniform in temperature across regions that seem too far apart to have ever been in contact? Why is the geometry of space so close to perfectly flat? The leading solution, cosmic inflation, proposes that the universe underwent exponential expansion in its first moments, stretching tiny regions to cosmic scales. But Magejo and Albrecht suggested a different possibility. What if light traveled much faster in the early universe? If phi was enormous during the first moments after the Big Bang, then distant regions of the universe could have been in causal contact, even without inflation. Information and energy could have traveled across the early universe fast enough to establish the uniform temperature we observe today. As the universe evolved, and fundamental physics settled into its current form, the speed of light gradually decreased to its present value. This idea requires us to think carefully about what we mean by the speed of light. In physics, E appears in numerous equations and relationships. It's not just the speed at which photons travel, it's the fundamental conversion factor between space and time, the maximum speed of causality, and a crucial parameter in the strength of electromagnetic interactions. If C changes, many other aspects of physics must change as well. One way to make VSL theories work, mathematically, is to allow other fundamental constants to vary alongside the speed of light. The fine structure constant, which determines the strength of electromagnetic interactions, might increase as T decreases, keeping certain physical relationships stable. The gravitational constant might also evolve, ensuring that the overall behavior of matter and energy remains consistent with what we observe. Evidence for variable light speed would likely come from astronomical observations of distant objects. Since light from distant galaxies left them billions of years ago, we're seeing these objects as they existed when the universe was much younger. If the speed of light was different then, it might leave detectable signatures in the light itself. Subtle changes in spectral lines, unexpected relationships between distance and brightness, or violations of physical laws that we assume to be universal. Some researchers have claimed to find such evidence. Studies of quasar absorption lines, the shadows cast by gas clouds in the light from distant quasars, have suggested that the fine structure constant might have been slightly different billions of years ago. If confirmed, this could indicate that fundamental constants do evolve over cosmic time, though it wouldn't necessarily prove that the speed of light itself has changed. The implications of variable light speed extend far beyond cosmology. If K was much larger in the early universe, then EMMC curve suggests that even small amounts of matter contained vastly more energy than they do today. This could help explain how the universe generated enough energy to drive inflation, or create the matter-antimatter asymmetry that allows ordinary matter to exist. Particle physics could also be revolutionized by VSL theories. Many of the fundamental forces of nature become unified at extremely high energies, suggesting that they were once aspects of a single superforce. If the speed of light was different when these forces were unified, it might provide new insights into how symmetry breaking occurred as the universe cooled and the forces separated into their current forms. String theory, which attempts to unify all fundamental forces including gravity, naturally accommodates variable fundamental constants. In string models, the constants of physics are determined by the geometry of extra dimensions. As the universe evolves, these extra dimensions could change size or shape, causing the constants to evolve as well. Some string models predict that the speed of light should decrease over cosmic time, though usually by amounts too small to detect with current technology. Laboratory tests of VSL theories focus on precision measurements of fundamental constants over time. If the speed of light is decreasing, then atomic clocks based on different physical processes should drift relative to each other as time passes. Extremely precise atomic clocks, some accurate to better than 1 part in 1018, have been monitoring potential changes in fundamental constants for years. So far they've found no evidence for variation, but they've only been operating for decades rather than the billions of years over which cosmic changes might occur. Geological and astronomical evidence provides longer baselines for testing constant variation. The decay rates of radioactive elements depend on fundamental constants, so ancient radioactive minerals could preserve evidence of different physics in the distant past. Natural nuclear reactors that operated billions of years ago, like the one discovered in Gabon, Africa, provide particularly stringent tests because nuclear reaction rates are extremely sensitive to the values of fundamental constants. Some of the strongest constraints on variable light speed come from studies of Type 1a supernovae, stellar explosions that serve as standard candles for measuring cosmic distances. These explosions are powered by nuclear physics that depends sensitively on fundamental constants. The fact that distant supernovae from billions of years ago appear to follow the same physical laws as nearby ones suggests that fundamental constants haven't changed dramatically over cosmic time. Fourier cell theories also face theoretical challenges. Einstein's relativity is built on the assumption that the speed of light is constant, so allowing causality to vary requires modifications to our most successful theory of gravity. These modifications must be carefully constructed to preserve the parts of relativity that work extremely well while allowing for the new physics needed to make light speed variable. One approach involves scalar fields, hypothetical energy fields that pervade space and can vary from place to place and time to time. These fields could interact with photons and other particles in ways that effectively change the speed of light while preserving the underlying structure of relativity. The Higgs field, which gives particles their mass, is one example of how scalar fields can influence fundamental physics. Though the Higgs doesn't directly affect light speed, alternative theories of gravity such as those proposed by John Barrow and other theorists incorporate variable constants from the ground up. These theories often make predictions that differ slightly from Einstein's relativity, providing potential tests that could distinguish between constant and variable speed of light scenarios. The philosophical implications of VSL theories are profound. If fundamental constants can change, then the laws of physics themselves might be evolving. The universe we observe today could be just one phase in a much longer story of cosmic evolution, where the rules governing reality shift and change over time, scales so vast they dwarf human experience. This possibility raises questions about the nature of physical law itself. Are the constants of physics truly fundamental, or are they emergent properties of some deeper, more dynamic reality? If they can change, what determines their values at any given time? Could conscious observers somehow influence the evolution of fundamental constants? Or are we simply along for the ride in a cosmos whose rules are still being written? Current evidence suggests that if the speed of light has changed over cosmic time, the changes have been small and subtle. But even small changes could have dramatic implications for our understanding of the universe's history and future. As our instruments become more precise and our theoretical understanding deepens, we may finally determine whether the speed of light truly deserves its status as nature's most fundamental constant, or whether it's just another parameter in an ever-evolving cosmic story. Chapter 24. Artificial light, natural law, even laser beams and quantum pulses obey the same cosmic rule. Human technology has given us unprecedented control over light. We can generate laser beams billions of times brighter than the sun, create pulses of light lasting only femtoseconds, and manipulate individual photons with quantum precision. We can bend light around corners, slow it to a crawl, and even bring it to a complete stop. With such mastery over electromagnetic radiation, it's tempting to think we might eventually find ways to make light travel faster than its natural speed limit. But every experiment reveals the same humbling truth. No matter how cleverly we design our devices, or how exotic the conditions we create, all light, artificial and natural alike, obeys the same cosmic speed limit. The most powerful lasers on Earth demonstrate this principle dramatically. The National Ignition Facility in California can generate laser pulses with peak powers exceeding 500 trillion watts more power than the entire United States consumes, concentrated into beams narrower than human hairs and pulses shorter than the time it takes light to cross a grain of sand. Yet, despite this incredible intensity, every photon in these beams travels at exactly the same speed as the gentle light from a candle flame. 2099,792,458 meters per second in vacuum. This constancy holds regardless of how the light is produced. LED lights, fluorescent bulbs, and incandescent filaments all generate photons through different mechanisms. Quantum transitions in semiconductors, excited gas atoms, and thermal radiation from hot objects. The colors differ, the intensities vary wildly, and the production methods have nothing in common. Yet every photon emerges traveling at exactly the speed of light. It's as if nature has stamped this single velocity onto every electromagnetic wave, regardless of its origin or energy. Laser physics provides particularly striking examples of light's uniform behavior. In a laser, millions of atoms emit photons in perfect synchronization, creating coherent beams where all the light waves march in lockstep. This coherence allows lasers to maintain their focus over vast distances and concentrate enormous amounts of energy into tiny spots. But coherence doesn't change the fundamental speed of the light itself. Whether photons are emitted randomly by thermal sources or in perfect coordination by laser systems, they all propagate at exactly the same velocity. The development of ultra-fast laser technology has pushed our control over light to remarkable extremes. Femtosecond lasers can generate pulses of light lasting less than 100 femtoseconds, shorter than the time it takes light to travel the width of a human hair. These pulses are so brief that they can freeze molecular motion and capture chemical reactions as they happen. Some experimental systems have achieved attosecond pulses lasting only a few hundred attoseconds, timescales so short that light travels only a few hundred nanometers during the entire pulse. Yet even these incredibly brief bursts of light obey the speed limit. The pulse as a whole might last only femtoseconds, but every photon within it travels at the standard light speed. The shortness of the pulse comes from precisely timing when photons are emitted, not from making individual photons travel faster. It's like having a very short train pass by at normal speed. The train is brief, but each car moves at the same velocity. Quantum optics has revealed even more exotic forms of artificial light that still respect the cosmic speed limit. Scientists can now create squeezed light, where quantum uncertainty is redistributed between different properties of photons, single photon sources that emit exactly one photon at a time, and entangled photon pairs that share mysterious quantum correlations. These quantum states of light have properties that would have seemed magical to earlier generations of physicists, yet they all propagate at exactly the speed of light. Even more remarkably, scientists have learned to manipulate the speed of light itself, or rather to control how fast light propagates through specially prepared materials. In certain ultra-cold atomic gases, researchers have slowed light pulses to speeds of only a few meters per second, slower than a bicycle. Some experiments have brought light to a complete stop, storing optical information in atomic spins and later releasing it as light beams. Other studies have made light appear to travel faster than C by manipulating how wave packets propagate through materials with unusual optical properties. These dramatic demonstrations might seem to violate the cosmic speed limit, but they actually confirm it in subtle ways. When light slows down in special materials, individual photons still travel at the speed of light between atoms. The overall pulse appears slower because the light is constantly being absorbed and re-emitted by atoms in the material, creating delays that reduce the average propagation speed. It's like a relay race where each runner maintains normal speed, but the baton is delayed at each handoff. Similarly, when light appears to travel faster than light in certain materials, what's actually happening is that the peak of the light pulse reconstructs itself ahead of where it would normally be. This effect involves the interference of many different wavelengths of light and cannot be used to transmit information faster than C. The leading edge of the light pulse, the first indication that light is coming, still travels at exactly the speed of light. Nature preserves causality, even when allowing these exotic propagation effects. Fiber optic communications provide a massive real-world demonstration of light's consistent behavior. Internet signals travel as pulses of laser light through optical fibers spanning continents and ocean basins. These systems carry tremendous amounts of information, terabytes per second, through single fibers, yet every bit of data travels at the same fundamental speed. The delays we experience in international phone calls and internet connections reflect the time required for light to cross vast distances, not any variation in light speed. Modern telecommunications engineers must account for light's finite speed in their designs. Synchronizing signals across continental networks requires precise timing corrections for the light travel delays between different locations. High-frequency trading systems locate their computers as close as possible to stock exchanges, because even the few microseconds required for light to travel extra distances can mean millions of dollars in a fast-moving market. These practical applications demonstrate that light's speed limit isn't just an abstract physical principle. It's a concrete constraint that shapes our technological civilization. The consistency of light speed across all artificial sources and conditions reflects deep principles of symmetry and relativity. The speed of light in vacuum is the same regardless of the motion of the source or observer, a principle that Einstein elevated to a fundamental postulate of special relativity. This means that light from a laser on a speeding spacecraft appears to travel at exactly the same speed as light from a stationary laboratory laser, as measured by any observer in an inertial reference frame. This symmetry principle has been tested with extraordinary precision using artificial light sources. Experiments have measured light speed from sources moving at various velocities, from laboratory lasers mounted on rotating platforms to starlight from binary star systems where one star moves toward us while its companion moves away. In every case, the measured speed of light remains constant within experimental uncertainty. Perhaps most remarkably, even the most exotic artificial light sources we can imagine would still obey the cosmic speed limit. Hypothetical gamma-ray lasers operating at energies millions of times higher than visible light would still emit photons traveling at exactly c. Theoretical X-ray lasers using nuclear transitions instead of atomic ones would produce the same result. Even if we could somehow harness the energy of black holes or neutron stars to create artificial light sources, every photon would emerge traveling at the standard speed of light. This universality extends to light generated by the most extreme artificial processes we can conceive. Particle accelerators create intense beams of synchrotron radiation when they bend the paths of near-light speed electrons and protons. This artificial light spans the entire electromagnetic spectrum from radio waves to gamma rays, and it's generated by particles moving at 99.99999% of light speed. Yet every photon in this radiation travels at exactly c, regardless of the extreme energies and velocities involved in its creation. The development of artificial light sources has also revealed subtle aspects of how the speed of light relates to other physical constants. When engineers design lasers, they must account for the relationship between light speed, wavelength, and frequency. The equation C(L) speed equals wavelength times frequency holds absolutely for all artificial light, providing a fundamental constraint that shapes everything from the design of optical cavities to the spacing of atoms in laser-gain media. Quantum cascade lasers, which create light through carefully engineered quantum transitions in semiconductor structures, demonstrate how precisely we can control light emission while still being bound by the speed limit. These devices can be designed to emit at almost any desired wavelength by adjusting their internal structure at the nanometer scale. Yet, regardless of wavelength, color, or emission mechanism, every photon emerges at the same speed. The precision of modern atomic clocks, which use laser light to probe atomic transitions, depends critically on the constancy of light speed. These clocks work by measuring the frequency of light absorbed by atoms in precisely defined energy transitions. If the speed of light varied even slightly, these frequency measurements would become unreliable, and our most precise timekeeping would be impossible. The fact that atomic clocks maintain their precision over years of operation provides indirect but powerful evidence that artificial light obeys exactly the same speed limit as natural light. Even attempts to create faster-than-light effects with artificial light sources confirm the fundamental speed limit. Experiments with negative group velocity make light pulses appear to exit a material before they fully enter it, but careful analysis shows that no information actually travels faster than c. The peak of the pulse might be reconstructed ahead of its normal position, but the leading edge of the light signal, the first indication that light is present, always travels at exactly the speed of light. Scientists have also created artificial light with exotic polarization states, orbital angular momentum, and other unusual properties. Some experiments generate light beams that spiral through space like corkscrews, carrying orbital angular momentum that can be transferred to microscopic particles. Others create light with polarization states that change in complex patterns as the beam propagates. These unusual forms of light have found applications in quantum computing, optical manipulation, and advanced communication systems. Yet, despite their exotic properties, every photon in these beams travels at the standard light speed. The constancy of light speed for artificial sources has profound implications for our understanding of physical law. It suggests that the cosmic speed limit is truly fundamental, not a property of particular types of light or specific emission mechanisms, but a feature of spacetime itself. Whether light comes from the nuclear furnace of a star, the quantum transitions in a laser, or the thermal radiation from a light bulb, It encounters the same geometric constraints imposed by the structure of spacetime. This universality also highlights the deep connection between technology and fundamental physics. Every laser, LED, and optical fiber in our modern world operates according to the same principles that govern starlight and cosmic rays. The engineers designing tomorrow's optical technologies must work within the same speed limit that constrained the first photons emitted in the early universe. Human creativity can find countless ways to generate, manipulate, and control light, but it cannot change the fundamental speed at which light propagates through space. The study of artificial light has thus become a vast experimental program testing one of physics' most fundamental principles. Every laser pulse, every optical communication system, and every precision measurement using light provides additional confirmation that the cosmic speed limit applies universally. The more sophisticated our light sources become, the more precisely we can verify that nature's speed limit holds under all conditions. In the end, our mastery over artificial light reveals not human dominance over natural law, but our growing appreciation for the elegant simplicity underlying physical reality. No matter how complex our light sources or how exotic the conditions we create, the speed of light remains constant, a testament to the deep mathematical harmony that governs both artificial technologies and cosmic phenomena. Chapter 25: Why Light's Limit Might Be the Universe's Greatest Gift. How the ceiling of speed creates structure, order, and meaning in everything. At first glance, the speed of light seems like a cosmic speed limit imposed to frustrate our ambitions. It confines us to our tiny corner of the galaxy, makes interstellar travel practically impossible, and ensures that the vast majority of the universe will forever remain beyond our direct reach. But this perspective misses a profound truth. The speed of light isn't a barrier that constrains the universe, it's the foundation that makes the universe possible at all. Far from being a cosmic inconvenience, the light speed limit might be the single most important feature that allows complexity, structure, and meaning to exist. Consider what the universe would look like without a maximum speed for information and causality. If influences could propagate instantaneously across any distance, cause and effect would lose all meaning. Every event would instantly affect every other event throughout the cosmos. The gravitational pull from distant galaxies would change Earth's orbit instantaneously when stars were born or died. The electromagnetic radiation from every source in the universe would arrive simultaneously, creating an incomprehensible cacophony of signals with no temporal structure. In such a universe, the very concept of locality, the idea that events are primarily influenced by their immediate surroundings, would be meaningless. Chemistry would be impossible because atomic interactions would be instantly overwhelmed by influences from distant cosmic events. Biology couldn't evolve because organisms would be bombarded by simultaneous signals from every corner of the universe. The delicate processes that build complex structures from atoms to galaxies to living beings require isolation from distant influences and the ability to develop gradually over time. The speed of light creates what physicists call light cones, the boundaries that separate events that can influence each other from those that cannot. These light cones provide the fundamental structure that makes causality possible. When you make a decision right now, it can only affect events within your future light cone, the expanding sphere of space that light from your current location can reach. Similarly, your present state can only be influenced by events within your past light cone, the converging sphere of space from which light could have reached you. This causal structure creates islands of relative independence throughout the universe. While distant galaxies certainly affect each other through gravity and electromagnetic radiation, these influences propagate at light speed, giving local regions time to develop their own characteristics before external influences arrive. The Milky Way galaxy has had billions of years to evolve its spiral structure, form stars and planets, and nurture the development of life. Partly because influences from distant galaxy clusters take billions of years to cross the intervening space. The finite speed of light also creates the possibility of stable structures by limiting the rate at which information can be integrated. Consider the human brain, which processes information through networks of neurons connected by synapses. If neural signals could travel instantaneously, the brain would be overwhelmed by simultaneous inputs from all regions at once. The finite speed of neural transmission, much slower than light, but fast enough for biological processes, allows the brain to integrate information sequentially, creating the temporal structure necessary for thought, memory, and consciousness. At cosmic scales, the light speed limit enables the formation of galaxies, star systems, and planets, by preventing gravitational influences from overwhelming local dynamics. When a massive star collapses to form a black hole, the gravitational waves from this event propagate outward at light speed, affecting distant objects gradually rather than instantaneously. This allows nearby matter to respond and reorganize while distant regions continue their evolution undisturbed, until the influence finally reaches them. The speed of light also makes possible the phenomenon of cosmic horizons, boundaries beyond which we cannot see or be influenced. The observable universe has a finite radius, because light from more distant regions hasn't had time to reach us since the Big Bang. This might seem like a limitation, but it's actually essential for the existence of stable cosmic structures. If we could see and be influenced by the entire infinite universe simultaneously, the energy density and gravitational effects would likely prevent the formation of stars, galaxies, and life. In physics, the speed of light serves as the crucial parameter that relates space and time, energy and momentum, electric and magnetic fields. Without this fundamental speed, the equations of relativity would lose their meaning, and the universe would lack the geometric structure that makes physical law possible. The speed of light is woven so deeply into the fabric of space-time that removing it would unravel the mathematical foundations upon which all physical phenomena depend. The quantum mechanical world also depends critically on the light speed limit. Quantum field theory, which describes the behavior of fundamental particles, requires a maximum speed for the propagation of quantum information. Without this limit, quantum fields couldn't maintain the locality properties that make particle interactions predictable. The delicate balance between quantum uncertainty and relativistic causality that underlies all of particle physics would collapse without the speed of light to maintain proper relationships between space-time and quantum phenomena. For biological systems, the speed of light provides the perfect balance between connection and isolation. Organisms need to respond to their environment, but not so quickly that they're overwhelmed by every distant event. The speed of light ensures that biological processes can operate on appropriate timescales fast enough to respond to immediate threats and opportunities, slow enough to allow for complex information processing and decision-making. The development of complex chemistry also depends on the light speed limit. Chemical reactions proceed through sequences of molecular interactions that must happen in specific orders to produce desired products. If electromagnetic influences could propagate instantaneously, these reaction sequences would be disrupted by simultaneous interactions with distant molecules, making complex chemistry impossible. The finite speed of light provides the temporal structure necessary for the step-by-step processes that build complex molecules and ultimately life itself. In terms of information and computation, the speed of light creates natural limits that may be essential for intelligence and consciousness. Any information processing system, whether biological brain or artificial computer, requires time to integrate inputs, perform calculations, and generate outputs. If information could propagate instantaneously, these temporal processes would lose their structure, making complex computation impossible. The speed of light provides the fundamental timing mechanism that allows information to be processed sequentially, rather than simultaneously. The speed of light also enables the existence of distinct perspectives and subjective experiences. If information traveled instantaneously, all possible observers would share identical knowledge about the state of the universe at every moment. There would be no private thoughts, no personal memories, no individual experiences. The finite speed of light creates informational boundaries that allow for the existence of separate minds, with unique perspectives and experiences. At the larger scales, the light speed limit may be essential for the universe's long-term evolution and the possibility of infinite complexity. If influences could propagate instantly, the universe might quickly reach thermodynamic equilibrium, with all energy evenly distributed and no gradients remaining to drive further change. The finite speed of light ensures that different regions of the universe can maintain different energy densities and continue evolving for vast periods of time. The speed of light also creates the possibility of surprise and discovery. If we could instantly know the state of the entire universe, there would be nothing left to explore or understand. The light speed limit ensures that information reaches us gradually, creating an ongoing process of discovery as light from distant events finally arrives after traveling for millions or billions of years. Every night, telescopes capture photons that began their journeys when the universe was young, bringing us news of cosmic events that happened long before Earth existed. Perhaps most profoundly, the speed of light makes possible the existence of meaning itself. Meaning emerges from relationships between events, from patterns that develop over time, from the interplay between cause and effect. If everything happened instantaneously everywhere at once, there would be no temporal structure to create meaning. The speed of light provides the temporal scaffolding upon which significance, purpose, and understanding can develop. In this light, the speed of light reveals itself not as a cosmic constraint, but as the fundamental gift that makes existence itself possible. It creates the boundaries within which complexity can flourish, the timing that allows meaning to emerge, and the structure that permits consciousness to contemplate its own existence. Rather than limiting the universe, the speed of light liberates it to become everything that it is, a cosmos rich with structure, teeming with life, and pregnant with infinite possibilities for growth, discovery, and understanding. The universe's greatest speed limit turns out to be its greatest enabler, the foundation upon which all the beauty, complexity, and wonder of existence rests.